Picture the equator on a clear day. Somewhere above the Pacific, a thick band of cloud hangs over water that turns sunlight into a soft, bright haze. In the tropics, the heat doesn't really leave. It just eases off for a few hours at night, then returns again. If Earth has a furnace, this is where it runs hottest. Now bury it in ice. Not thin ice, not a seasonal skin of frost. Kilometers of it. Old, grinding ice that stretches from pole to pole, sealing the oceans, choking the shorelines, pressing down on every shallow seafloor it can reach. That shimmering equatorial Pacific you just pictured, gone. In its place, a surface that reflects close to 80% of incoming sunlight back into space. Less heat absorbed, more ice survives, more light reflected. A feedback loop that feeds itself. This isn't a thought experiment. It happened, twice. Around 717 million years ago, Earth froze. Not like the ice ages we usually mean when glaciers creep outward from the poles and then retreat. This was something else. Something so extreme that when the evidence started coming together in the late 20th century, many geologists tried to kill the idea before they accepted it. But the rocks kept agreeing with each other. Australia, Namibia, the Gavalach Islands off the Scottish coast, the Canadian Yukon, the mountains of Colorado, glacial deposits where they shouldn't be, magnetic signatures locked into stone, iron-rich layers that don't fit a normal ocean, different continents, different teams, the same implication, ice at the equator, ice everywhere. And somehow, against every intuition about what that kind of cold should do, life made it through. That's the part that keeps people up at night. Not only the freezing, but the return. Because the world that came out of the second deep freeze around 635 million years ago wasn't the same world that went in. The oceans were chemically altered, the atmosphere shifted, and within a few tens of millions of years, a blink in deep time, the fossil record begins to hint at something new. Complex multicellular life, not just cells, actual bodies. The story of Snowball Earth can be told two ways. In one version, it's one of the worst crises life has ever faced. In the other, it's the kind of crisis that quietly reshapes what life is capable of. Both can be true. This is a story about feedback loops that don't stop on their own, about volcanoes doing patient work for millions of years, about survival under conditions that sound impossible until you see the evidence, and about an uncomfortable rule of evolution. Extreme pressure doesn't always erase complexity. Sometimes it filters for it. So we're going to move slowly. The Cryogenian lasted roughly 85 million years. We can afford to be careful. We'll stay close to the evidence, the chemistry, the layers, the odd rocks that only make sense once you learn their language. And we'll stay close to the scientists who spent years in places like the Namib Desert and along the Scottish coast, trying to turn fragments into a coherent timeline. The science is remarkable. The uncertainty is part of the story. We'll keep both on the table. If you want more of this kind of slow science, you can subscribe to Silence of the Earth. And if you feel like it, leave a comment with where you're listening from. Night shift, late apartment, quiet house. It's always interesting to know where these long stories land. Now, let's go back. Around 717 million years ago, the planet looked unfamiliar. A supercontinent was starting to loosen and crack. The sun was slightly dimmer, not dramatically, but measurably by about 6%. Most of the land sat near the equator, which sounds like an advantage, and for a long time it probably was. But in the background, the atmosphere was changing, slowly, chemically, and almost invisibly, until it wasn't. The cold was on its way. To understand why Earth froze, we have to understand the world it froze from. And it was not the Earth we recognize. There were no grasses, no trees, no insects, no fish, no animals of any kind. The land was bare rock and sediment, swept by wind and carved by rivers that had nothing to hold their banks together because roots had not yet been invented. The The sky was a different color depending on how you interpret the haze. Some models suggest an atmosphere with enough methane and organic particulates to give the upper layers a pale amber tint, though on a clear day at the surface it would have appeared broadly blue. The oceans were full of microbial life, cyanobacteria, single-celled eukaryotes, stromatolite mats building up in shallow water. But the surface of the planet was, to any eye that might have looked at it, almost entirely dead. This was the Tonian period, the age immediately preceding the Cryogenian, running from roughly 1 billion years ago to about 720 million years ago. And in the Tonian, the geography of the planet was organized around a single enormous landmass called Rodinia. Rodinia was not the first supercontinent, and it would not be the last. But its particular configuration, the way it assembled, where it sat on the planet, and crucially how it began to fall apart, set in motion a chain of events that would alter everything. At its peak, Rodinia held essentially all of Earth's continental crust in one mass, a landmass so large that its interior would have been an immense arid wasteland, utterly cut off from any moderating influence the oceans might provide. The coastlines were long and exposed to warm, humid, tropical air. The interior was dry, and the whole thing sat straddled across the equator. That last detail matters enormously. The equator receives more solar energy per unit of surface area than anywhere else on the planet. It's also where the atmosphere is wettest, where rainfall is highest, and where, if you have exposed silicate rock sitting in warm, humid conditions, the chemical reactions that draw carbon dioxide out of the atmosphere proceed at their fastest. This process, silicate weathering, is one of Earth's primary long-term carbon regulators. Rain slightly acidified by dissolved carbon dioxide falls on rock, reacts with calcium and magnesium silicates, and carries the products into rivers that eventually reach the sea, where the carbon ends up locked away in carbonate sediments on the ocean floor. It is slow, steady, and enormously effective over geological time. Under normal conditions, it's balanced by volcanic outgassing, which returns carbon dioxide to the atmosphere at a roughly equivalent rate. With Rodinia sitting in the tropics, silicate weathering was running at maximum efficiency. The conditions were almost designed for it. Enormous surface area of fresh continental rock, tropical humidity, warm temperatures accelerating reaction rates. Carbon dioxide was being stripped from the atmosphere at an elevated pace. And then, around 720 to 718 million years ago, something made it worse. The Franklin Large Igneous Province erupted across what is now northern Canada, a volcanic event of extraordinary scale that emplaced roughly 6 million square kilometers of fresh basaltic rock. To put that in perspective, that's approximately twice the size of modern India, covered in new volcanic material. Fresh basalt is chemically reactive and weathers rapidly. Much of this basalt was deposited in exactly the wrong place, equatorial latitudes in warm and humid conditions, precisely where weathering proceeds fastest. An eruption that might have been expected to add carbon dioxide to the atmosphere through initial outgassing instead accelerated the removal of carbon dioxide from it, because the sheer volume of fresh, reactive rock flooding the weathering system dwarfed whatever gases the volcanism itself had contributed. The atmospheric carbon dioxide concentration began to drop. It would have been imperceptible on any human timescale. Over 1 million years, over 10 million years, there would have been no obvious sign. The planet was still warm, the oceans were still full of life, the sky was still blue. But the numbers were falling, and the Earth's climate system has a threshold, a tipping point that once crossed cannot be uncrossed by any of the mechanisms that might slow the approach to it. At the time, the Sun was approximately 6% less luminous than it is today. That sounds like a small number, but it isn't. It represents a significant reduction in the energy reaching Earth's surface, partially compensated for by the greenhouse effect of a carbon dioxide-rich atmosphere. As that carbon dioxide slowly declined, the compensation weakened. The planet cooled, incrementally, over millions of years. polar ice sheets grew. And as they grew, they began to reflect more sunlight back into space, which cooled the planet further, which grew the ice sheets further. The trap was set. The only question was how far south the ice would reach before the feedback became self-sustaining. That question had an answer. It was approximately 30 degrees of latitude, the point at which, according to climate modeling first worked out by the Soviet geophysicist Mikhail Budiko in 1969, the ice albedo feedback loop becomes irreversible. Once glaciers spread to within roughly 25 to 30 degrees of the equator, the mathematics of planetary albedo take over. The ice reflects so much incoming solar energy that even a full tropical sun can no longer keep the equatorial surface warm enough to hold back the advance. The planet enters a runaway state. The ice was coming, and Rodinia, straddling the equator with its vast exposed silicate surfaces, had spent millions of years doing everything possible to make sure there would be nothing to stop it. What happened next would last 57 million years. The atmosphere does not announce when it is changing. There is no threshold you cross, no visible sign, no moment when the sky shifts color or the wind picks up differently. Carbon dioxide is invisible, odorless, and present in concentrations so small, even at elevated Precambrian levels, that no organism alive at the time would have perceived its decline. What the atmosphere does is change the math. Quietly, over millions of years, it adjusts the numbers that govern how much heat stays near the surface and how much escapes into space. And when those numbers cross certain values, the planet reorganizes itself accordingly. By the time the cryogenian began, the math had been changing for a long time. The story starts with rain, not the dramatic kind, not the storms that strip hillsides and flood river valleys, but the ordinary persistent rain that falls across tropical landscapes and soaks into soil and runs slowly through rock. Rainwater absorbs carbon dioxide from the air as it falls, forming a weak solution of carbonic acid. When that acidic water contacts silicate minerals in continental rock, the feldspars, the pyroxenes, the vast families of calcium and magnesium silicates that make up most of the crust, it reacts with them. The minerals dissolve slowly. The calcium and magnesium ions enter the groundwater and flow downstream toward the sea, and the carbon that was briefly carbonic acid ends up eventually precipitated on the ocean floor as calcium carbonate, limestone, dolostone, locked away from the atmosphere for millions to hundreds of millions of years. This is silicate weathering. It is one of the oldest and most reliable carbon sinks on the planet, and it has been running continuously for over 3 billion years. Under normal conditions, it operates in rough balance with volcanism. Volcanoes and mid-ocean ridges return buried carbon to the atmosphere as carbon dioxide. Silicate weathering takes it back out. The system oscillates within a range that keeps the planet habitable. Warmer when carbon dioxide is high, cooler when it drops, but self-correcting. When temperatures rise, weathering accelerates, pulling more carbon dioxide down and cooling the climate. When temperatures fall, weathering slows, carbon dioxide builds up, and the planet warms again. It is an elegant feedback loop, and it has kept Earth from either boiling or freezing permanently for most of its 4 billion year history. What happened in the late Tonian was a disruption to that balance. Not a sudden one, but a sustained one that lasted long enough to overwhelm the corrective mechanism. Rodinia's continental crust, clustered in the tropics, was running the weathering reaction at abnormally high rates. The warm, wet conditions of the equatorial zone maximized how quickly silicate minerals dissolved and released their carbon into the ocean atmosphere system's sink. On its own, this would have been a slow, manageable drawdown, the kind of thing the volcanic outgassing rate might have compensated for over geological time, as it had done many times before. But around 718 million years ago, the Franklin Large Igneous Province added a new variable: 6 million square kilometers of fresh basalt, emplaced across equatorial latitudes, saturated the weathering system with reactive rock at exactly the moment when the system was already running fast. Fresh basalt weathers far more readily than older continental rock. The surface area available for chemical reaction increased dramatically, and volcanic outgassing from the Franklin event itself, while significant in the short term, was not enough to offset the enormous additional sink that 6 million square kilometers of fresh reactive basalt represented over the following millions of years. The carbon dioxide concentration in the atmosphere began a sustained decline. A 2024 study from researchers at the universities of Adelaide and Sydney modelled the tectonic processes of the late Tonian in detail, focusing on something that had received relatively little attention in earlier analyses: the output rate of mid-ocean ridge volcanism. Mid-ocean ridges, the underwater mountain chains where tectonic plates spread apart and new ocean floor is created, are responsible for a substantial fraction of Earth's long-term volcanic carbon dioxide output. The rate at which they produce new crust determines, in part, how much carbon they return to the atmosphere. During the breakup of Rodinia, as the supercontinent fragmented and its pieces drifted apart, the geometry of mid-ocean ridge systems changed. The Adelaide and Sydney team found that this reorganization resulted in an exceptionally low outgassing rate from mid-ocean ridges, approximately 9 megatons of carbon per year, well below later averages. The volcanic side of the carbon balance, in other words, had gone quiet precisely when the weathering side was accelerating. It was the combination of these factors, elevated weathering from Rodinia's tropical position, the additional reactive surface of the Franklin basalts, and the reduced volcanic return from quieter mid-ocean ridges, that drove the atmospheric carbon dioxide concentration down far enough to matter. The models suggest this was not a rapid event by any standard. It played out over tens of millions of years. Carbon isotope records from sedimentary rocks of this age show a gradual positive shift in the ratio of carbon-13 to carbon-12, consistent with an atmosphere steadily losing carbon dioxide as biological productivity ran its carbon through the ocean floor burial pathway. The signal is there, written in rock, legible to anyone with the tools to read it. As carbon dioxide fell, the greenhouse effect weakened. The planet's surface temperature dropped, degree by imperceptible degree. Polar ice sheets, which had probably been absent or minimal through much of the warmer Tonian, began to grow, and as the ice grew, it introduced the second factor, the one that would turn a slow, manageable cooling into something altogether different. Ice reflects sunlight, open ocean absorbs it. The difference between the two surfaces in terms of how they handle incoming solar energy is substantial. Sea ice and glacial ice have an albedo, a reflectivity, of roughly 70 to 90%. Ocean water has an albedo closer to 6%. Every square kilometre of ocean surface that freezes over stops absorbing solar energy and starts reflecting it. The planet's energy budget shifts. Less heat stays in the system. The temperature drops, more ocean surface freezes. This is the ice albedo feedback. It is not complicated. It does not require unusual chemistry or rare geological circumstances. Given enough ice, it runs itself. The question in the late Tonian and early Cryogenian was where the feedback would stop. Under ordinary glacial conditions, the kind Earth has experienced repeatedly over the past few 100 million years, the ice advance reaches some equilibrium latitude and halts. The tropics stay warm enough to prevent the ice from spreading further. The feedback stabilizes. The Earth of 717 million years ago was not operating under ordinary conditions. The Sun was 6% dimmer than it is today. Carbon dioxide had been falling for millions of years. The continents were concentrated at low latitudes, maximizing weathering and minimizing the polar land area that, in later ice ages, would anchor ice sheets at higher latitudes before they could threaten the tropics. The climate system had less resilience than it would in later eras. Less greenhouse gas, less solar input, less geographic configuration to keep the tropics reliably warm. The threshold, as Mikhail Budyko had calculated in 1969, using the best climate models then available, sat somewhere around 25 to 30 degrees of latitude. If glaciers advanced to within that range of the equator, the ice albedo feedback would become self-sustaining. The tropics would no longer be warm enough to arrest the advance. The remaining ice-free ocean would cool, freeze, and add its reflectivity to the feedback. The planet would, in a geologically brief interval, become entirely ice-covered. In the late Tonian, with carbon dioxide declining and the sun dim and the continents in the wrong place, the glaciers were moving south. They had not crossed the threshold yet, but the gap between where they were and where they needed to be to trigger a runaway was closing year by year, millennium by millennium, in a planetary scale process so slow it would have been invisible to any observer watching in real time. The sedimentary record from this period preserves the approach, isotope ratios shifting, the first appearance of glaciogenic sediments at mid-latitudes, the early signs of a planet beginning to lose its grip on warmth. The crossing came around 717 million years ago. The exact trigger, whether it was a particularly cold century, a temporary spike in weathering from fresh rock exposure, a slight dip in volcanic output, is not preserved in the record with sufficient resolution to identify. What the record shows is the result: glacial deposits, globally distributed, at latitudes that should have been tropical. The threshold had been crossed. The feedback had engaged. What came next had no precedent in Earth's history before it, and nothing quite like it has happened since. There is a particular kind of catastrophe that does not announce itself. It builds quietly, through increments so small that each one, taken alone, would register as ordinary variation. A slightly cooler decade, a glacier that advances a little further than usual before retreating, a carbon dioxide reading that trends imperceptibly downward over 1,000 years. The individual steps are unremarkable. What makes them catastrophic is the direction they establish, and the feedback mechanism waiting at the end of that direction. The ice albedo feedback is one of the most consequential mechanisms in Earth's climate history. Ice and snow are highly reflective surfaces. When sunlight strikes a glacier, most of it bounces back into space rather than being absorbed. Open ocean, by contrast, is one of the darkest natural surfaces on the planet. It absorbs roughly 94% of the solar energy that hits it. The difference between these two surfaces, in terms of their effect on the planet's energy budget, is enormous. Every square kilometre of ocean that freezes converts a surface that was absorbing energy into one that is rejecting it. The system loses heat. The planet cools. More ocean freezes. This is the feedback in its simplest form. It is self-reinforcing in one direction only. Once ice spreads, it creates conditions that cause more ice to spread, and it has no natural ceiling except the limits of how far ice can physically reach. In a climate system already under stress, already running with less greenhouse gas than it needs to stay warm, already receiving less solar energy than it will in later eras, the ice albedo feedback is not just a contributing factor, it is a trap. Mikhail Budyko understood this in 1969. The Soviet geophysicist was working with energy balance models, mathematical frameworks that track how much solar energy enters the climate system, how much is reflected, and how much is retained as heat. And what his calculations revealed was a threshold. At roughly 25 to 30 degrees of latitude, the feedback crosses a point from which there is no return. Ice at that latitude receives enough sunlight that its high reflectivity, multiplied across the surface area available at those latitudes, offsets the warming influence of even a tropical sun. The tropics cannot hold. The remaining ice-free ocean cannot stay warm enough to arrest the advance. The planet enters a state that Budyko recognized as theoretically stable and deeply alarming. He called it a runaway glaciation. His models showed three possible stable states for Earth's climate: an ice-free world, a partially glaciated world with ice caps at the poles, and a completely ice-covered world. The middle state, partial glaciation, was stable only within a certain range. Push the ice past a critical latitude and the partial state became unstable. The system would not find a new equilibrium at 50 degrees or 40 degrees. It would run all the way. Boudicca's result was treated with some skepticism when it was first published. The idea that Earth could theoretically freeze solid seemed to strain credibility, and the practical question of how a completely frozen planet could ever thaw again added another layer of apparent impossibility to the scenario. His models were also simplified. They could not capture the full complexity of ocean circulation, atmospheric dynamics, or the role of sea ice versus land ice in different latitude bands. Later, more sophisticated climate models refined the threshold and softened some of the sharper edges of his conclusions, but the fundamental result held. There is a latitude at which the ice albedo feedback becomes self-sustaining. Cross it, and the planet reorganizes. In the early cryogenian, with carbon dioxide declining and the sun running 6% below its modern output, the glaciers were advancing. Not dramatically, not in any way that would have been visible from year to year or century to century. Ice sheets grow through the slow accumulation of snow that does not fully melt in summer, compressing under its own weight over thousands of years into the dense, blue-white material that geologists can identify in the rock record hundreds of millions of years later. At mid-latitudes, where ice sheets first establish themselves in a cooling world, the process is measured in geological time. But measured in geological time, it was moving fast. MIT researchers working with coupled ocean atmosphere models found that a drop of approximately 2% in incoming solar radiation, sustained over roughly 10,000 years, was sufficient to push the climate system past the runaway threshold, given the cryogenian boundary conditions. 2% over 10,000 years is not a dramatic perturbation. It is well within the range of variability that normal geological processes, slight changes in volcanic output, short-term orbital variations, fluctuations in weathering rates, could produce without any extraordinary event. The cryogenian climate was, by the standards of later Earth history, unusually vulnerable. The margins were thin. What the ice albedo feedback does, once it engages beyond the critical latitude, is change the timescale. The slow, million-year process of carbon dioxide drawdown gave way to something faster. Each year that the ice advanced, the planet's reflectivity increased. Each increase in reflectivity reduced the amount of solar energy retained. Each reduction in retained energy cooled the surface further and allowed the ice to advance more. The feedback ran on its own momentum, accelerating as the ice spread toward lower latitudes where the incoming solar energy was higher, and the contrast between ice-covered and ice-free surfaces was therefore more extreme. The equatorial surface temperature during full glaciation has been estimated at approximately -33 degrees Celsius, roughly 60 degrees colder than the modern equatorial average. To put that in terms that map onto lived experience, the warmest place on a fully glaciated Earth would have been colder than the interior of Antarctica today. The ocean surface at the equator, normally the warmest water on the planet, would have been locked under ice. The atmosphere above it, deprived of evaporative input from the ocean, would have been dry and brutally cold, circulating in patterns that bear little resemblance to the convective, moisture-rich, tropical circulation of the modern world. The planet's albedo, its overall reflectivity, would have reached somewhere around 60 to 70%. Today, it sits around 30%. The difference represents an enormous change in how much solar energy the Earth retains. A planet with that albedo, receiving sunlight from a sun 6% less luminous than the modern one, would have been locked in a deeply stable cold state. The same feedback that drove it there now worked to keep it there. Any small warming, a mild volcanic winter ending, a slight increase in solar output, would have been insufficient to melt enough ice to darken enough surface to shift the energy balance. The stable state was ice. This is what makes Snowball Earth different from ordinary glaciations. It is not a matter of degree. An ice age in the conventional sense, the Pleistocene glaciations of the past 2 million years, for instance, operates within a range where the feedback is bounded. The tropics stay warm. The equatorial ocean stays open. The system oscillates between glaciated and interglacial states, driven by orbital cycles, and never approaches the threshold at which the tropics themselves come under ice. Snowball Earth crossed that threshold. The feedback had no natural bound. It ran to completion. The geological record preserves this crossing with remarkable clarity. Glacial deposits, diamictites, dropstones, striated pavements, appear at paleolatitudes that, when corrected for continental drift, place them within 10 degrees of the cryogenian equator. The magnetic minerals in those rocks recorded the orientation of Earth's magnetic field when the sediments were deposited, and that orientation places the deposits within the tropics beyond any reasonable uncertainty. The evidence for equatorial glaciation is not inferential. It is direct, physical, and distributed across every major continent. The ice reached the equator around 717 million years ago. Everything that followed, the 57 million years of frozen ocean, the survival of life in conditions that seem incompatible with life, the slow volcanic rescue, and the world that emerged afterward, began at that moment. At the crossing of a threshold that Boudico had identified mathematically in 1969, working from first principles in a Soviet research institute, decades before anyone had found the rocks that would confirm what his equations implied. The feedback had engaged. The planet was committed. 57 million years is a number that requires some assistance to become real. The dinosaurs existed for approximately 165 million years, from the late Triassic through the end of the Cretaceous, ruling every terrestrial ecosystem on Earth across that entire span. The Sturcian glaciation lasted more than a third of that. Our own genus, Homo, has been on the planet for somewhere between 2 and 3 million years, depending on how you draw the taxonomic lines. The Sturcian lasted roughly 25 times longer. Every civilization humanity has ever built, every language ever spoken, every war ever fought, every technological development from the first stone tool to whatever exists right now, all of that history fits inside a fraction of the time the Sturtian glaciation persisted. It began around 717 million years ago. It ended around 660 million years ago. In between, the Earth was encased in ice. The name comes from the Sturt Formation, sequences of glacial rock exposed in the Flinders Ranges and surrounding basins of South Australia, where some of the world's best preserved cryogenian sedimentary records sit in outcrops that you can walk up to and touch. These rocks were among the first studied in detail by geologists trying to understand the Snowball Earth hypothesis, and they remain central to the ongoing effort to reconstruct what conditions on the frozen planet actually looked like. The formation itself is named for Charles Sturt, the 19th century British explorer who crossed the region in the 1840s, though Sturt had no idea what the rocks beneath his feet recorded. He was looking for an inland sea. He found desert. What the rocks told, it would take another century and a half to understand. The global extent of the Sturtian glaciation was not established until 2010, when Francis MacDonald and his colleagues at Harvard published a synthesis of geological and paleomagnetic data from multiple continents showing that glacial deposits of Sturtian age occur at paleolatitudes within 10 degrees of the cryogenian equator. The evidence came from North America, from Africa, from Australia, from Asia, different continents, different rock types, different depositional environments, all preserving the same signature of tropical glaciation within the same narrow time window. The Sturtian was not a regional event, it was planetary. What did that planet actually look like? The global average surface temperature has been estimated at somewhere around -50 degrees Celsius. though reconstructing a single number for a planet-wide average across 57 million years involves uncertainty at every step. What the models and geochemical data converge on is a surface cold enough to sustain kilometre-thick ice sheets at the equator, cold enough to freeze the ocean's surface globally, and cold enough to suppress nearly all evaporation from what little liquid water might have persisted in protected environments. The atmosphere would have been dry, Arctic dry, in a way that modern experience with dry climates does not quite prepare you for. The hydrological cycle, which on a modern Earth moves an enormous volume of water between ocean and atmosphere every year, would have been reduced to a fraction of its current activity. Less evaporation means less precipitation. Less precipitation means less snow feeding the glaciers, which sounds like it should limit their growth. But the ice was already there, already stable, already maintained by the reflectivity feedback rather than by ongoing accumulation. The cold was self-sustaining. The ocean beneath the ice is where things become genuinely strange. Once the global ice cover was established, the ocean surface was cut off from the atmosphere. No gas exchange, no light penetrating below the first few centimeters of ice. The photosynthetic organisms that depend on sunlight for energy, the cyanobacteria, the early eukaryotic algae that had been thriving in Tonian seas, lost their primary energy source wherever the ice was thick enough to block light entirely. Carbon dioxide, normally regulated by the balance between atmospheric and oceanic concentrations, began to accumulate differently. Oxygen, produced by photosynthesis and consumed by respiration, dropped in the ocean interior as biological productivity collapsed and the supply from surface exchange was cut off. Iron tells part of this story. Under normal ocean conditions, iron released from hydrothermal vents on the seafloor gets oxidized almost immediately when it reaches oxygen-containing water, precipitating out of solution. During the Sturtian, with the ocean sealed beneath ice and oxygen depleted in the deep water, iron had nowhere to go. It accumulated, dissolved in the cold, dark, increasingly anoxic ocean interior for millions of years. The result, when the ice eventually melted and oxygenated surface water mixed with the deep ocean again, was a massive precipitation of iron oxide that produced the banded iron formations found in Sturtian Age rock sequences on multiple continents. These formations, the Rapitan Group in the Canadian Yukon, the Urucum deposits in Brazil, sequences across the Damara Belt of southern Africa, are among the most striking geological records of the Sturtian. Within their layered structure, they carry a detailed archive of what the ocean was doing while the ice was present. A 2021 study from Southampton found something unexpected in those layers. By analysing the magnetic properties of Sturtian banded iron formations in unprecedented detail, the team identified cyclical variations in the rock record that match the known frequencies of Earth's orbital cycles: the roughly 26,000-year precession cycle, the 41,000-year obliquity cycle, the 100,000-year eccentricity cycle. These are the same Milankovitch cycles that drive the glacial-interglacial oscillations of the Pleistocene. The fact that they appear in Sturtian sediments means that Earth's climate system, even while locked in a global glaciation, was still responding to orbital forcing. The ice sheets were waxing and waning slightly in response to cyclical changes in solar input. Ice-free patches were periodically opening and closing in response to those same cycles. The planet was frozen, but it was not dead. The climate machinery was still running, even if the range of outputs it could produce was drastically narrowed. This finding matters for a reason that goes beyond the details of Sturtian stratigraphy. One of the persistent challenges to the Snowball Earth hypothesis has been explaining how life survived. A completely static, frozen planet with no open water and no functional climate cycles is very difficult to reconcile with the absence of a mass extinction in the cryogenian fossil record. The Southampton study's evidence for ongoing orbital cycling. For a planet that was frozen but dynamic, with periodic fluctuations creating temporary opportunities for liquid water, for light, for the biological activity that the fossil record implies was continuing, helps resolve that tension. The Sturtian was not 57 million years of unchanging cold. It was 57 million years of a constrained, oscillating, deeply cold system that maintained just enough variability to keep life from disappearing entirely. A 2026 study from the same institution pushed this further. By analysing 2,600 individual varve layers, thin annual sediment bands deposited in glacial lake sequences from the Port Ascaig Formation in Scotland, the team found evidence for seasonal freeze-thaw cycles continuing throughout the Sturtian. Varves form through the same mechanism in ancient lakes that they form in modern ones. Coarser sediment settles during warmer months when meltwater is actively transporting material, and finer sediment settles during winter when the lake surface is frozen and water movement is minimal. The fact that recognizable varve sequences exist in Sturtian deposits means that seasons were still occurring. Summer still melted some ice, winter still refroze it. The rhythm of the year, however compressed and cold, had not been erased. The Port Ascaig Formation in the Gavelach Islands off the Scottish coast is, in several respects, the most complete Sturtian record on the planet. The formation is 1.1 kilometers thick, over a kilometer of layered sedimentary rock recording the Sturtian from its earliest stages through its full extent. At its base, immediately below the first glacial deposits, the rocks preserve Tonian-age tropical shallow water carbonates, evidence of a warm, carbonate-producing sea that existed at these latitudes immediately before the ice arrived. The contact between those warm water sediments and the overlying glacial rock is sharp. Whatever transition occurred happened fast enough, in geological terms, to leave no gradual record of cooling between the two environments. One moment, or rather, one interval too short to preserve, the Gavelach region was a tropical sea. The next, it was under ice. The Sturtian ended around 660 million years ago. What caused the termination is a question the next chapters will address directly, because the mechanism of escape from Snowball Earth is one of the most extraordinary stories in planetary science. But the ending, when it came, was geologically abrupt. The same kind of rapid transition that marked the onset, leaving a sharp boundary in the rock record between glacial deposits and the cap carbonates that signal the return of a warmer ocean. In between onset and termination, separated by 57 million years of frozen ocean and compressed, cold seasons and iron accumulating in the dark, life waited. It did not wait passively. The fossil record of the Cryogenian presents a problem that took decades to fully appreciate. Here is the problem. Nothing died, not nothing. That would be too simple. The Cryogenian fossil record is sparse, as you would expect from a period when biological productivity collapsed and the environments most likely to preserve organic material were buried under kilometers of ice. But the lineages survived. The eukaryotes that existed before the Sturtian glaciation, the single-celled organisms with complex internal architecture, the early multicellular algae, the microbial communities that had been building stromatolite mats in shallow Tonian seas, were present in some form on the other side. Molecular clock studies, which use the rate of genetic mutation to estimate when evolutionary lineages diverged, consistently place major eukaryotic diversification events before the Sturtian, not after it. The branches were already there. The freezing did not cut them. This is not a trivial observation. A global average temperature of -50 degrees Celsius, an ocean sealed under ice, cut off from sunlight and atmospheric oxygen, its chemistry drifting toward the anoxic iron-rich conditions that the banded iron formations record in such detail. Conditions that, on the face of them, seem incompatible with the survival of complex cellular life, and yet the life survived. The question of where and how is one of the most actively researched problems in Neoproterozoic biology, and the answers that have emerged over the past 2 decades are stranger and more varied than anyone initially expected. The most straightforward refuge was the deep ocean floor. Hydrothermal vents, the seafloor fissures where geothermally heated water rich in dissolved minerals emerges into the cold ocean, operate entirely independently of solar energy. They were present in the cryogenian ocean as they are present today, and the ecosystems they support run on chemical energy rather than light. Sulfur-oxidizing bacteria, methane-producing archaea, communities of chemosynthetic organisms built around the energy gradient between hot vent fluid and cold seawater. These are not exotic organisms living at the edge of possibility. They are robust, ancient lineages that predate the evolution of photosynthesis and have been running their chemistry in the dark for billions of years. The Snowball Earth event, however catastrophic at the surface, would not have reached the deep vent communities in any direct way. The ocean floor was cold, anoxic, and iron-rich, unusual conditions by later standards, but not inherently hostile to organisms that had never depended on either oxygen or light. Subglacial environments offered a different kind of refuge, where continental ice sheets sit on rock containing radioactive elements. The slow decay of those elements generates heat. Where tectonic activity brings magma close to the surface, geothermal flux can maintain liquid water beneath ice sheets even in extreme cold. The modern analogues are well documented. Beneath the Antarctic ice sheet, a network of liquid water lakes sits isolated from the surface, some of them having been cut off from any contact with the atmosphere for millions of years. When researchers finally drilled into Lake Whillans in 2013 and Lake Mercer in 2018, they found microbial communities, not sterile water, but active biological ecosystems sustained by the oxidation of minerals in the surrounding rock. The same conditions would have existed beneath cryogenian ice sheets, wherever geological heat prevented the basal ice from freezing solid. The surface of the ice itself is a less obvious candidate, but recent research has made it a serious one. A 2025 study published in Nature Communications took a direct experimental approach to the question of Snowball Earth surface refugia by analysing meltwater ponds on the McMurdo ice shelf in Antarctica, shallow pools that form each austral summer on the ice surface when solar heating melts the top layer. These ponds are cold, nutrient-poor, and subject to complete freezing during winter. They are, in many respects, as close an analogue to the surface conditions of equatorial Snowball Earth as the modern world provides. The research team applied lipidomics, the systematic analysis of lipid molecules, and molecular genetic techniques to characterize the biological communities living in these ponds. What they found was a diverse assemblage of eukaryotic organisms, including algae and heterotrophic protists, surviving and reproducing in conditions that most laboratory assessments of minimum survivable parameters would classify as marginal. The mechanism that makes surface meltwater ponds possible on a frozen equatorial planet involves dust, wind-transported mineral dust derived from exposed land surfaces at mid-latitudes or from volcanic eruptions, settles onto the ice surface and darkens it locally. Dark patches absorb more solar energy than clean ice, warming slightly above the surrounding surface. Under a tropical sun, even a cryogenian sun 6% less luminous than today's. Those dark patches can reach temperatures sufficient to melt the top layer of ice during the warmest part of the year, creating shallow pools that persist through summer and freeze again in winter. The pools are small, they are cold, they are chemically unusual. They are also, as the McMurdo data suggest, biologically viable. For equatorial ice during the Sturcian, the geometry works. The tropics receive more solar radiation per unit area than higher latitudes even under snowball conditions. A dust-darkened patch of equatorial ice, exposed to near overhead summer sun, could maintain liquid surface water in an environment where the surrounding ice is tens of degrees below freezing. The pools would have been isolated from each other, scattered across an ice surface the size of a world ocean, each one a separate biological experiment running its own chemistry with whatever organisms happen to be present. The diversity of modern McMurdo pond communities, despite those ponds being equally isolated and equally subject to seasonal freezing, suggests that isolation alone is not a disqualifying condition for biological persistence. The geochemical record from China adds another dimension. Black shale sequences in the Nantuo Formation, deposited in what were, at the time, open water marine environments at paleolatitudes of roughly 30 to 40 degrees north, contain the organic signatures of photosynthetic organisms. Photosynthesis requires light. Light requires open water, or at least thin enough ice to allow sufficient penetration. The presence of photosynthetic biomarkers in Marinoan age sediments at those latitudes has been used to support the slushball interpretation of Snowball Earth. That interpretation holds that a narrow band of thin or seasonally open water persisted near the equator throughout the glaciation, a continuous refuge for light-dependent life, rather than the scattered episodic pools of the meltwater pond model. The honest position, given the current state of evidence, is that multiple refugee types probably operated simultaneously. Deep vent communities sustained chemosynthetic life without any reference to surface conditions. Subglacial lakes maintained microbial ecosystems wherever geothermal heat was sufficient. Surface meltwater ponds provided seasonal habitats for photosynthetic and heterotrophic eukaryotes on the ice surface. And if the slushball interpretation is correct, if some open water persisted near the equator, then a continuous marine habitat existed throughout the Sturtian, constrained and cold and chemically unusual, but present. What none of these refugia provided was abundance. The cryogenian fossil record is sparse not just because preservation is difficult under glacial conditions, but because there was genuinely less life, less total biomass, less primary productivity, fewer habitats, smaller populations, longer generation times under cold-slowed metabolisms. Molecular clock estimates suggest significant population bottlenecks during this period. The lineages persisted, but they persisted at reduced numbers under conditions that maintained only what was necessary to keep the evolutionary thread intact. That thread, as it turned out, was enough. What the organisms that survived the Sturtian glaciation did not know, could not know, by any definition of knowing that applies to single-celled organisms, was that the conditions pressing them were selecting for something. Not intentionally, not directionally in any purposeful sense, but the physics of survival in cold, dark, nutrient-poor environments imposes its own logic on what kinds of organisms can persist, and that logic, accumulated across 57 million years of pressure, was working quietly on the raw material of future complexity. The ice held, the life held, and somewhere beneath the frozen surface, in hydrothermal darkness or dusty equatorial meltwater pools or thin equatorial seas, the organisms that would eventually become everything continued their work of staying alive. There is a layer of rock in the Flinders Ranges of South Australia that changes colour in alternating bands, red and grey, repeated over and over across outcrops that stretch for kilometres through the desert hills. The bands are thin, millimetres to centimetres each, and they stack in sequences that can run to several metres thick before the pattern gives way to something else. Local geology students are taken to see them as part of their training. Tourists stop on the roadside to photograph them. The colours are striking. What the colours mean is stranger than most visitors realise. Those bands are iron. Specifically, they are iron oxide, the same chemistry as rust, precipitated from seawater at the bottom of a cryogenian ocean during the Sturtian glaciation. Each red band is a pulse of oxidized iron that settled out of the water column at a moment when oxygen reached the deep sea. Each grey band is a period when it didn't. The alternation between them records, in chemical sediment, the rhythm of an ocean responding to conditions unlike anything the planet had experienced in over 1 billion years. Banded iron formations, BIFs in the shorthand of the literature, are among the oldest and most studied rock types on Earth. Their main period of formation runs from roughly 3.5 billion years to about 1.8 billion years ago, the early history of photosynthesis. Cyanobacteria were first producing oxygen in quantities sufficient to react with the iron dissolved in Archean and early Proterozoic seas, and the result was iron precipitation on a geological scale. That iron had been accumulating for billions of years, leached from seafloor rocks by hydrothermal activity, held in solution in a deep ocean that had no free oxygen to react with it. When photosynthesis changed the chemistry of the surface ocean, pulses of oxygenated surface water mixing into the depths triggered iron precipitation on a massive scale. The result was the vast BIF deposits of the Pilbara Craton in Western Australia, the Hamersley Range, the Superior Province across Canada, and the northern United States, ancient rust-coloured rock that now provides most of the world's iron ore. After about 1.8 billion years ago, BIFs essentially stopped forming. The ocean had been progressively oxygenated. The reservoir of dissolved iron that photosynthesis kept consuming had been depleted enough that there was no longer sufficient dissolved iron in the deep ocean to precipitate in meaningful quantities when oxygen arrived. For over 1 billion years, BIF deposition was absent from the geological record. Then the Sturtian glaciation began, and they came back. The reappearance of BIFs in cryogenian age rock sequences is one of the most diagnostic signatures of Snowball Earth conditions, and understanding why they came back requires understanding what the ice cover did to the ocean's chemistry over the course of 57 million years. The ocean floor was never frozen. Hydrothermal vents continued operating throughout the Sturtian, releasing iron-rich, chemically reduced fluid into the water column as they had always done. Under normal ocean conditions, that iron would have been oxidized within a short distance of the vent, reacting with dissolved oxygen in the surrounding water, precipitating out of solution, settling to the sea floor as iron oxide minerals in quantities too small to form significant deposits. The process is fast. Iron doesn't stay dissolved in oxygenated seawater for long. Under snowball conditions, the surface was sealed. No oxygen was entering the ocean from the atmosphere. The photosynthetic organisms that had been producing dissolved oxygen in the photic zone were absent or vastly reduced in the deep ocean interior, operating only in whatever refugia allowed their survival at the surface. The deep ocean oxygen reservoir, cut off from its primary sources of replenishment, was being steadily consumed by the slow respiration of whatever organisms remained and by the chemical reactions between reduced volcanic inputs and any remaining oxidants in the water. Over millions of years, the deep ocean became progressively anoxic, oxygen depleted, rich in dissolved iron and other reduced chemical species, chemically resembling the Archean Ocean of 3 billion years prior in ways that startled geologists when they first recognized the signature in cryogenian rocks. Iron accumulated, not in small amounts. Over 57 million years of continuous hydrothermal input into an ocean that could not oxidize it, the dissolved iron concentration in the deep Sturtian Ocean reached levels that had not existed since before the Great Oxidation Event. The ocean was, in the language of geochemistry, a reducing environment, chemically opposite to the oxygen-rich, iron-depleted modern ocean, a vast reservoir of dissolved, reduced iron waiting for the conditions that would cause it to precipitate. Those conditions arrived when the glaciation ended. Meltwater from the retreating ice sheets, oxygenated by contact with the now exposed atmosphere, flooded into the ocean. The mixing of that oxygen-bearing surface water with the iron-saturated deep water triggered rapid, massive iron precipitation. The same basic chemistry as the Archean BIFs, operating on a compressed timescale. The result was the Sturtian BIF deposits that appear on every major continent that preserves this part of the geological record. The Rapitan Group in Canada, the Urucum in Brazil, the Kingston Peak Formation in California, sequences across Africa and Australia. The layering within those deposits tells a more detailed story than the simple fact of their existence. The 2021 Southampton study that identified orbital cycles in Sturtian BIF sequences did so by measuring magnetic susceptibility, a property of the rock that varies depending on the type and abundance of iron minerals present, at intervals of a few centimeters through the entire thickness of the formation. What emerged from that measurement series, when the researchers analyzed it for periodic signals, were cycles matching the known frequencies of Earth's orbital variations with a precision that left little room for alternative explanations. The approximately 26,000-year precession cycle, the 41,000-year obliquity cycle, the 100,000-year eccentricity cycle, all present in the iron chemistry of a cryogenian ocean sealed under ice. What this means, concretely, is that the rate of iron precipitation in the deep Sturtian ocean was varying in response to orbital forcing, to small, cyclical changes in how much solar energy the frozen surface received at different points in Earth's orbital path. Those changes were enough, even through kilometers of ice, to alter the climate at the surface slightly. Ice sheets waxed and waned, meltwater inputs to the ocean varied. Mixing between oxygenated surface environments and the iron-rich deep changed in response to those surface fluctuations. And each change in mixing left a chemical signal in the settling iron oxide minerals that now, 700 million years later, a research team in Southampton could read. The BIFs are not just a record of what the Sturtian ocean contained. They are a record of how the climate system continued to function, constrained, compressed into a narrow range of outputs, but still responding to orbital cycles, as it has always done. The planet was frozen, and the planet was still a planet, still governed by the same physics, still cycling through the same astronomical rhythms. What the BIFs also record is the scale of the chemical transformation that the Sturtian glaciation produced in the ocean. 57 million years of iron accumulation. 57 million years of anoxia deepening as the reduced inputs continued and the oxidized reserves were consumed. By the time the Sturtian ended and the ice began to retreat, the ocean was not the same ocean that had been sealed under the ice at the beginning. It was chemically altered in ways that would take millions of years to fully equilibrate. The iron, the anoxia, the altered carbon and sulfur and phosphorus cycles all carrying consequences that extended long after the last glacial deposit was buried under cap carbonate. The equatorial sea would eventually return to something resembling warmth. The chemistry it carried would not return to what it had been before. The bands of red and grey in the Flinders Ranges are not just pretty, they are the ocean's record of what it endured, and embedded within their layering, the still legible signal of a sky that kept moving overhead even when no surface creature could have looked up to watch it. Science does not accept extraordinary claims on the basis of a single line of evidence, and Snowball Earth is an extraordinary claim. The idea that the equator was glaciated, that ice sheets sat within 10 degrees of latitude of a region that today averages 28 degrees Celsius, requires the kind of evidence that rules out alternative explanations one by one from multiple independent directions. The remaining possibilities have to reduce to one. That process took decades. It involved geologists on 4 continents working with techniques that ranged from classical field observation to paleomagnetic analysis to uranium-led geochronology, and it is still, in some of its details, ongoing. What follows is not a complete account of every piece of evidence. It is an account of how the case was built, and why, by the early 21st century, it had become difficult to argue against. The first kind of evidence is the most direct, the rocks themselves. Glacial deposits have a distinctive character that geologists have been reading for nearly 2 centuries, ever since Louis Agassiz argued in the 1840s that much of northern Europe had been shaped by ice rather than by Noah's flood. Glaciers do things to sediment that other geological processes do not. They grind rock into a fine powder called rock flour, They carry boulders hundreds of kilometers from their sources and deposit them in places where no river could have delivered them. They scratch and polish the bedrock beneath them, leaving parallel grooves called striations that record the direction of ice movement. And when glaciers carve into the ocean, icebergs carry the debris embedded in their base ice across open water and drop it, as the ice melts, into marine sediments far from any land source. These ice-rafted boulders, dropstones, settle into fine-grained marine muds and deform the sediment layers beneath them in a characteristic way that cannot be replicated by any non-glacial process. Cryogenian-age rocks on every major continent preserve these signatures. Diamictites, the unsorted chaotic mixtures of fine matrix and coarse clasts characteristic of glacial till. Dropstones in fine-grained marine sequences. Striated pavements beneath glacial deposits. And above all of them, the cap carbonates that sharply overlie each sequence, marking the termination of glaciation. The distribution of these deposits across continents that were in the Cryogenian, located at very different positions than they occupy today, is itself significant, but distribution alone does not prove that the glaciation was global. Glacial deposits at high paleolatitudes would be unremarkable. The critical question was always about latitude, specifically how far from the equator these deposits were when they formed. This is where paleomagnetics becomes essential. When sediments are deposited and eventually lithify into rock, the magnetic minerals within them, primarily magnetite and hematite, align with Earth's magnetic field at the time of lithification. The orientation of those minerals is then locked in place as the rock solidifies. Crucially, the inclination of the magnetic field varies with latitude in a predictable way. Field lines are nearly horizontal at the equator and nearly vertical at the poles. By measuring the inclination of remnant magnetism in ancient rocks, the angle at which the fossil magnetic minerals are tilted relative to the horizontal, geologists can calculate the latitude at which those rocks formed, corrected for any subsequent tilting of the rock itself by later geological deformation. This technique is not perfect. Ancient magnetic fields may have differed from the modern dipole in ways that introduce uncertainty. Rocks can acquire secondary magnetism through later chemical alteration, potentially overprinting the primary signal. Continental drift means that the rocks have moved, sometimes substantially, since they formed, and reconstructing their original positions requires independent constraints from plate tectonic models. Each of these issues has to be assessed separately for every study, and the uncertainties compound. A single paleomagnetic result from a single formation is suggestive. Consistent results from multiple formations on multiple continents, all pointing to the same low-latitude paleo positions, are something much stronger. The Ediacaran Formation in South Australia provided some of the earliest and most compelling paleomagnetic results. Deposited during the Marinoan Glaciation, the Ediacaran Formation preserves glacial sediments that, by paleomagnetic analysis, formed at a paleolatitude of approximately 4 to 6 degrees from the Cryogenian equator. 4 degrees. The modern equivalent would be glacial deposits forming in Sumatra or in the Amazon basin. The result was first published in the 1980s and has been revisited and refined multiple times since, consistently returning low-latitude results. The formation also preserves tidal rhythmites, thin sediment layers recording the fortnightly and monthly tidal cycles of a shallow sea, which independently confirm a low-latitude depositional environment, since tidal patterns at the equator are distinctive and measurable in the sediment record. In 2010, Francis MacDonald at Harvard and his colleagues published a synthesis that moved the case to a different level of certainty for the Sturtian specifically. By combining paleomagnetic data with uranium-led geochronology, high-precision radiometric dating that can place volcanic ash beds within glacial sequences to within 1 million years or less, the team demonstrated that Sturtian glacial deposits occur at paleolatitudes within 10 degrees of the equator on multiple continents simultaneously. The simultaneity matters. Regional glaciations at low latitudes are conceivable under unusual local conditions. A globally synchronous glaciation at low latitudes, dated to the same narrow window on every continent, is not easily explained by anything other than a global event. The Port Ascaig Formation in the Gavelach Islands off the Scottish coast adds a dimension that purely geochemical or paleomagnetic evidence cannot provide. A continuous stratigraphic record of the transition from pre-glacial conditions to full glaciation and, in the uppermost part of the formation, back again. The formation is 1.1 kilometers thick. At its base, warm water Tonian carbonates record an environment that was, by every available indicator, a tropical shallow sea, the kind of carbonate-producing environment that exists today on the Bahamas platform or on the Great Barrier Reef. Above that contact, which is sharp enough to suggest that the transition from tropical sea to glaciated environment happened faster than the sedimentary record can resolve, come 1.1 kilometers of glaciogenic sediments recording the full span of the Sturtian. The formation is uniquely complete because the Scottish continental fragment that carries it was, in the Cryogenian, positioned at a paleolatitude of roughly 5 to 10 degrees north, well within the tropics. It has since experienced relatively little tectonic disruption, preserving the full thickness of Sturtian age deposits in unusual continuity. A 2024 study of the Port Ascaig Formation focused on the contact zone between the pre-glacial carbonates and the overlying glacial deposits, the exact boundary at which the world changed. High-resolution sampling across that boundary, combined with chemostratigraphic analysis of carbon isotope ratios, showed the same negative delta-13 carbon excursion seen in equivalent sequences worldwide, a sharp drop in the carbon-13 to carbon-12 ratio immediately preceding the onset of glaciation. It reflects the collapse in biological productivity that accompanied the ice advance, and it appears in Scotland at the same time it appears in Namibia, in China, in Australia. The signal in Scotland matches the signal in Namibia, in China, in Australia. The chemistry of the ocean changed globally, and it changed at the same time everywhere the record is preserved. In 2025, researchers working in the Rocky Mountains of Colorado announced a different kind of evidence from a different kind of environment. The Thaw injectites, bodies of sandstone injected under high pressure into the surrounding granite of Pikes Peak, had been known to geologists for years, but their age and origin had been debated. New dating placed their formation in the Cryogenian, and the injection mechanism most consistent with the geometry and pressure required to force sand into fractured granite was meltwater trapped beneath an ice sheet, pressurized by the weight of ice above it and forced into available fractures in the underlying rock. Subglacial meltwater injection. In Colorado, at a continental interior location far from any coastline, at a time when the evidence from every other continent places the world in the depths of the Sturtian glaciation. It was the first direct evidence that the Cryogenian ice sheets extended across continental interiors, not just to the coastlines where glacier marine sediments are most readily preserved, but into the deep interior of land masses that, in the Cryogenian arrangement of the continents, sat squarely within the tropics. Each of these lines of evidence, the paleomagnetics, the dropstones, the geochronology, the chemostratigraphy, the subglacial injection structures, was developed by different research groups using different methods in different parts of the world over a span of 4 decades. None of them, taken alone, would be conclusive. Taken together, pointing in the same direction from every angle the investigation could approach, they describe a planet that was unambiguously glaciated to its equator. Twice. Paul Hoffman spent 50 months in the Namibian desert over the course of his career, collecting samples from outcrops that no road reached and that no other researcher had examined in sufficient detail. He was not trying to confirm a hypothesis. He was trying to understand what the rocks said. What they said, eventually, was unambiguous. The equator was under ice. The evidence said it clearly enough. The equator was under ice, had been for 57 million years, and then slowly it wasn't. The Sturtian ended around 660 million years ago. The mechanism of that ending is a story for the next chapter. What matters here is what followed the ending, and what happened not long after to undo it. When the Sturtian ice retreated, it left behind a planet that was, by any measure, extraordinary. The atmosphere was dense with carbon dioxide that had accumulated during 57 million years of suppressed weathering. Volcanic outgassing with nowhere to go, building up against a sealed planetary surface until conditions changed. The ocean was chemically disrupted, flooded with meltwater, turbulent with the mixing of iron-rich deep water and newly oxygenated surface water. The cap carbonates were forming, thick, globally distributed carbonate layers precipitating rapidly from a supersaturated ocean. A geological event so abrupt and so widespread that it would eventually serve as one of the primary stratigraphic markers of Snowball Earth terminations. And somewhere in the shallow coastal seas and meltwater environments of the newly exposed continental margins, the organisms that had survived the Sturtian were beginning to move into an ocean they had not encountered in over 50 million years. The interglacial that followed lasted somewhere between 10 and 30 million years, depending on the location and the precision of the dating. Those numbers carry more uncertainty than the geochronology of the glacial events themselves, partly because the sedimentary record of the interglacial is less distinctive, and partly because correlating non-glacial sequences across continents is harder than correlating the sharp, globally synchronous signals of glacial onset and termination. What the record shows, wherever it is preserved in sufficient detail, is a warm interval with elevated atmospheric carbon dioxide, active carbonate deposition in tropical seas, and what appears to be a genuine radiation of multicellular algae. The first unambiguous fossils of organisms with differentiated cells and macroscopic body plans appear in sediments dated to this period. Life, in other words, had begun to explore what complexity could look like, and then the ice came back. The Marinoan glaciation began around 650 million years ago. Its causes are not as well constrained as those of the Sturtian, in part because the interglacial sedimentary record that would preserve the detailed geochemical signature of carbon dioxide decline is patchier, and in part because the Marinoan has received somewhat less focused geochronological attention than its predecessor. What the data indicate is that the same fundamental mechanisms were at work: carbon dioxide drawdown through silicate weathering, a climate system with insufficient greenhouse buffering to prevent glacial advance to low latitudes, and an ice albedo feedback that, once triggered, ran to completion. The planet had demonstrated that it could reach this state. Nothing had fundamentally changed the boundary conditions that made it vulnerable. The interglacial interval had let the ocean and atmosphere partially equilibrate, but not enough to insulate the climate system against a second crossing of the critical threshold. The Marinoan lasted approximately 15 to 20 million years, shorter than the Sturtian by a factor of 3 or more, but by no standard short. The glacial deposits it left are found on every continent that preserves cryogenian stratigraphy, and their paleolatitudes, where the paleomagnetic data are of sufficient quality, place them at equatorial positions consistent with a second global glaciation. The cap carbonates that overlie the Marinoan glacial deposits are among the thickest and most extensively studied in the cryogenian record, in some locations reaching 200 meters. Their chemistry records the same ultra-greenhouse aftermath that followed the Sturtian: rapid carbonate precipitation from a carbon dioxide-saturated ocean in the immediate wake of deglaciation. The Ediacaran Formation, whose Marinoan age glacial deposits provided some of the strongest paleomagnetic evidence for equatorial glaciation, is capped by the Nucalina Formation dolostone in South Australia, a cap carbonate sequence that has been sampled and analysed in detail for decades. The Nucalina preserves tubestone stromatolites, unusual columnar structures that grew upward through the carbonate as it precipitated, and large wave ripples recording the action of powerful ocean surface currents in the immediate aftermath of glaciation. Those wave ripples have been interpreted as evidence for dramatically enhanced trade winds driven by the extreme temperature gradient between the still cold poles and the rapidly warming tropics during deglaciation. A planet in violent thermal transition, its atmosphere reorganizing around a new energy budget as the ice retreated. What distinguishes the Marinoan from the Sturtian in the geological record is not just duration, but chemistry. The carbon isotope record preceding the Marinoan onset shows a particularly pronounced negative excursion, a sharp drop in delta-13 carbon that persists through much of the Marinoan glacial interval itself. This signal, known in the literature as the Trezona anomaly, for the Australian formation where it was first studied in detail, reflects a collapse in the biological carbon pump. That pump is the process by which photosynthetic organisms in the surface ocean fix carbon into organic matter that sinks to the seafloor, effectively removing it from the carbon cycle for geological timescales. When it shuts down, as it does when the surface ocean freezes, the isotopic ratio of carbon in seawater shifts toward lighter values. The Trezona anomaly is one of the most dramatic such excursions in the entire geological record, and its global distribution in pre-Marinoan and Marinoan age rocks is among the most convincing lines of evidence that the Marinoan was a planetary event, not a regional one. The sulfur isotope record adds a complementary signal. During the Marinoan, the ratio of sulfur isotopes in evaporate minerals and pyrite shifts in ways consistent with a deep ocean that was, as during the Sturtian, severely depleted in oxygen and rich in dissolved reduced sulfur species. The same anoxic sulfidic conditions that characterized the Sturtian deep ocean were reproduced during the Marinoan. The ocean sealed again, the same chemistry reasserting itself under similar physical boundary conditions. One aspect of the Marinoan that has attracted considerable attention is the speed of its termination. The cap carbonates overlying Marinoan glacial deposits are, if anything, more abrupt in their contact with the underlying diamictites than those of the Sturtian. Some sections show a transition from unambiguous glacial sediment to overlying cap dolostone with no visible gradation. No intermediate layer recording a gradual warming, no evidence of a prolonged transition. The geochemical models suggest that once the threshold carbon dioxide concentration required for deglaciation was reached, the ice albedo feedback ran in reverse as fast as it had run forward. The exposed, dark ocean surface absorbed solar energy. The temperature rose, more ice melted, more dark surface was exposed. The transition from fully glaciated to ice-free at the tropics may have taken as little as a few thousand years, a geological instant, leaving a contact in the rock record that looks, under close examination, almost like a boundary drawn with a knife. The Gasquia's glaciation, at approximately 580 million years ago, followed the Marinoan by roughly 55 million years. It was smaller, geographically more restricted, and shorter, lasting perhaps 1 to 2 million years, and is generally interpreted as a regional rather than global event, confined primarily to high and mid-latitudes. It left its own cap carbonates and its own isotopic signals, but the evidence for equatorial glaciation that defines the Sturtian and Marinoan is absent from the Gasquia's record. The planet was not a snowball at 580 million years ago. It was cold enough in some parts of the world for significant glaciation, but not cold enough or not configured correctly to cross the threshold into the runaway state. The Cryogenian as a whole, the two full snowball events and the interglacial between them, lasted from approximately 717 to 635 million years ago. 82 million years, give or take the uncertainties in the dating. Contained within those 82 million years were two complete cycles of planetary freezing and thawing, each driven by the same fundamental mechanisms operating on a climate system that was, by the standards of later Earth history, unusually vulnerable to them. The mechanisms of escape, the volcanic accumulation of carbon dioxide against a sealed surface, the eventual threshold crossing that reversed the ice albedo feedback, are what the next chapter addresses. But the Marinoan's legacy is not just geological. Its termination, around 635 million years ago, marks the beginning of the Ediacaran period, the first time in Earth's history that complex multicellular life would leave a substantial fossil record. What emerged from the second freeze was not the same ocean that had gone into it, and the organisms that would populate that ocean would not be the same organisms that had been waiting out the cold. Something had changed. Exactly what and why would take another 150 million years to fully express itself. There is a thought experiment worth sitting with before the mechanism of Snowball Earth's termination can be properly appreciated. Imagine the planet is sealed. Ice covers every ocean surface from pole to pole, kilometers thick at the poles and hundreds of meters thick even at the equator. The atmosphere above is cold and dry, stripped of most of the moisture that normally cycles through it because there is almost no evaporation from the frozen surface below. Silicate weathering, the primary long-term mechanism by which the atmosphere loses carbon dioxide, has slowed to a fraction of its usual rate because the rocks are buried under ice and the liquid water that drives the weathering reaction is largely absent from the continental surface. Into this sealed system, volcanoes continue erupting. They have no way of knowing that anything has changed. The mantle convects on timescales of tens to hundreds of millions of years, entirely indifferent to what is happening at the surface. Magma rises through the crust and erupts wherever the tectonic configuration allows it. Carbon dioxide exsolves from that magma and enters the atmosphere, as it has done continuously for the entire history of the planet, and it stays there. Under normal conditions, that carbon dioxide would be drawn back down within a few million years by silicate weathering and the biological pump, the twin mechanisms that keep atmospheric carbon in rough balance with volcanic input. Under snowball conditions, neither mechanism is operating at anything close to its normal rate. The carbon dioxide accumulates, year by year, millennium by millennium, million year by million year. It builds up in the atmosphere with no effective sink to remove it. The greenhouse effect strengthens, imperceptibly at first, then with increasing force as the concentration rises. This is the escape mechanism. It was identified by Joseph Kirschvink in his 1992 paper that coined the term Snowball Earth, the same paper that first presented the full hypothesis. And it remains the most widely accepted explanation for how a completely or near completely ice-covered planet manages to thaw itself. The planet cannot be rescued from outside. The sun is not going to get significantly brighter on any relevant timescale. The orbital cycles that drive Pleistocene glacial cycles cannot break a snowball. They are too small a perturbation against the enormous stabilizing force of planetary albedo at full glaciation. The rescue has to come from below. How long does it take? The answer depends on volcanic output rates, on how completely weathering was suppressed, and on exactly how much carbon dioxide is required to overwhelm the albedo feedback and initiate deglaciation. The numbers involved are large. Paul Hoffman's 1998 science paper estimated that something in the range of 350 times the modern atmospheric carbon dioxide concentration might be required, a figure that at modern volcanic output rates would take somewhere between 4 and 30 million years to accumulate. More recent modelling studies have refined those estimates, with some suggesting the required concentration may be somewhat lower, but the general picture remains. The escape from Snowball Earth was not quick. It was a slow, geological timescale process driven by the patient, indifferent operation of planetary volcanism against a climate system that was doing everything it could to stay frozen. The mid-ocean ridge system contributed to this process in a way that has received increasing attention in recent years. Submarine volcanism along mid-ocean ridges releases carbon dioxide directly into the deep ocean rather than into the atmosphere, but over geological timescales this carbon eventually equilibrates with the atmosphere. A 2016 study from the University of Southampton focused on the shallow portions of mid-ocean ridge systems during the Rodinia breakup, the same tectonic event that contributed to the onset of the Sturtian. As the supercontinent fragmented, new shallow ridge segments formed at the edges of the separating continental fragments. Those shallow ridges, erupting in relatively shallow water, produced hyaloclastites, glassy, fragmented volcanic rock formed when magma erupts into water and is rapidly quenched and shattered. Hyaloclastites alter chemically very quickly compared to deep water basalts, releasing calcium, magnesium and phosphorus into the overlying ocean water in large quantities. The Southampton study argued that this process, operating throughout the Sturtian glaciation as Rodinia continued to break apart, was progressively loading the ocean with alkalinity, with the chemical capacity to absorb and neutralize carbon dioxide. That preloaded alkalinity, accumulated over tens of millions of years, helps explain why the cap carbonates that formed after both glaciations were so thick and so widespread. The ocean was already chemically primed to precipitate carbonate on a massive scale the moment conditions allowed. The atmospheric carbon dioxide concentration required to initiate deglaciation has been modeled in detail. The ice albedo feedback that drives the glaciation also constrains what it takes to break it. Because the planetary albedo during full snowball conditions is so high, roughly 60 to 70% versus the modern 30%, even a substantially elevated greenhouse effect has less warming power per unit of carbon dioxide than it would in a partially glaciated world. The tropics are the key. Ice at the equator receives the highest solar input of any surface on the planet. As carbon dioxide rises and the greenhouse effect strengthens, the equatorial surface is the first place where the warming becomes sufficient to initiate melting. Once melting begins at the equator, the albedo feedback reverses. Dark ocean surface is exposed. That surface absorbs solar energy instead of reflecting it. The temperature at the equator rises further. More ice melts. The feedback runs in the same self-reinforcing way it ran during glaciation, only now in the opposite direction. The transition, when it came, was rapid by geological standards. Climate models of snowball deglaciation consistently produce very fast collapse of the ice cover once the threshold is crossed, potentially within a few thousand years for the final stage of equatorial deglaciation, after which the remaining high-latitude ice would have retreated over somewhat longer timescales. The geological record preserves this rapidity in the sharp contacts between glacial diamictites and overlying cap carbonates, contacts that show no gradual transition and no intermediate environment. One layer records glacial conditions. The next records a warm, carbonate-producing ocean. The time between them is too short to leave a visible sedimentary record. What the planet looked like during the brief interval of deglaciation is difficult to reconstruct in detail, but the broad outlines are preserved in the geochemistry of the cap carbonates themselves. The carbon dioxide concentration in the atmosphere at the moment of deglaciation would have been extraordinarily high. Some estimates place it between 10,000 and 100,000 parts per million, compared to the modern pre-industrial concentration of roughly 280. Rain falling through that atmosphere would have been intensely acidic, dissolving exposed rock at rates far beyond anything the geological record has recorded in calmer periods. That rain would have dissolved exposed rock at an extraordinary rate, flooding rivers and coastal seas with dissolved calcium, magnesium, and bicarbonate. The ocean, already alkaline from the accumulated weathering products of the glaciation and from the submarine volcanic loading, would have reached carbonate supersaturation almost immediately. Carbonate minerals, primarily dolomite in the earliest deposits, then calcite, precipitated rapidly from the water column and accumulated on the seafloor in the thick, distinctive layers that geologists now recognize as cap carbonates in outcrop after outcrop on every continent. The warming continued after the ice was gone. A planet with an atmosphere carrying 10,000 or more parts per million of carbon dioxide, receiving sunlight on a surface that no longer reflects most of it back to space, warms fast. The post-snowball greenhouse was intense. Some models suggest global mean temperatures may have briefly reached values well above anything in the subsequent geological record. A brief ultra-hothouse in the immediate aftermath of deglaciation before the weathering feedback reasserted itself and drew carbon dioxide back down over millions of years. In that ultra-hot house, with carbonate raining out of a warm, supersaturated ocean and acidic rivers delivering dissolved nutrients to coastal seas, the organisms that had survived the glaciation encountered something they had not experienced in 57 million years: an open world. Walk up to an outcrop of cap carbonate in the Flinders Ranges of South Australia, or along the dry riverbeds of northern Namibia, or in the exposed canyon walls of Svalbard. In each of these places, separated by thousands of kilometers, you will see the same thing: a pale, cream-colored carbonate rock sitting directly and sharply on top of dark gray or brown glacial sediment. No gradual transition between them. No thin intermediate layer recording a slow change. No evidence that anything mediated the boundary between a world locked in ice and a world warm enough to deposit carbonate. The contact is abrupt. It is, in many of the best preserved sections, almost knife-sharp, and it is the same everywhere. That contact is the most globally consistent event in the Cryogenian stratigraphic record. It appears on every continent that preserves rocks of this age, at locations that were, when the carbonates were deposited, scattered across the full range of latitudes from equatorial to subpolar. The cap carbonates are the planet's receipt for the Sturtian and Marinoan glaciations, the chemical signature of what happens when a world that has been holding its breath for tens of millions of years finally, rapidly exhales. The chemistry of that exhalation is recorded in the cap carbonates with unusual precision. In the first meters above the glacial contact, the cap carbonates are almost universally dolomitic, rich in the mineral dolomite, which requires specific chemical conditions for its formation and is generally interpreted in this context as evidence for precipitation from a shallow, evaporatively concentrated, carbon dioxide-saturated water. Above the dolostone, the cap carbonate typically transitions to limestone, calcite rather than dolomite, reflecting the progressive chemical evolution of the ocean as the carbon dioxide levels in the atmosphere began their long decline from the extraordinary post-glacial peak, and the ocean's chemistry adjusted accordingly. The two-layer structure of dolostone below and limestone above is repeated in cap carbonate sequences worldwide, a global stratigraphy that records the same ocean chemical transition playing out simultaneously across the entire planet. The Nucalina Formation in South Australia, the cap carbonate that directly overlies the Elatina Formation's Marinoan glacial deposits, has been studied in more detail than almost any other cap carbonate sequence in the world, and what it preserves is remarkable by any standard. Tubestone stromatolites grow through the lower dolostone layers in tight columnar clusters, their laminated internal structure recording rapid carbonate precipitation from the water column above. These are not ordinary stromatolites built by the slow accumulation of microbial mats over thousands of years. They grew fast, filling available space in a water column that was supersaturated with carbonate minerals and precipitating them almost as quickly as the water could supply them. Above the stromatolites, the Nucalina preserves something even more striking: giant wave ripples, not the centimetre-scale ripples that form under ordinary shallow water wave action, but structures spanning meters from crest to crest, recording wave energy far in excess of anything that operates in the modern ocean at equivalent water depths. The interpretation that has gained the most support is that these ripples formed under the influence of dramatically enhanced atmospheric circulation, trade winds and storm systems powered by the extreme thermal gradient between the still cold high latitudes and the rapidly warming tropics during the transition out of glaciation. A planet reorganizing its thermal structure in geologically near instantaneous time would have produced wind systems and wave energy unlike anything the modern ocean experiences, and the Nucalina's giant ripples are a preserved record of those conditions. The carbon isotope signal in cap carbonates is among the most extreme in the geological record. The delta-13 carbon values in cap dolostone worldwide are strongly negative, sometimes reaching values of -5 per mil or lower, in a geological context where values near zero are typical of carbonate rocks formed under normal ocean chemistry. These strongly negative values reflect a carbon cycle dominated in the immediate aftermath of deglaciation by inputs from sources depleted in carbon-13. Volcanic carbon dioxide is isotopically light. Organic carbon preserved in glacial sediments or frozen in permafrost through the glaciation would have decomposed and re-entered the cycle as the ice retreated. Methane release from destabilizing gas hydrates as the deep ocean warmed likely contributed as well. The signal is global. The same strongly negative delta-13 carbon values appear in cap carbonates from every continent that preserves them, confirming that the ocean chemistry that produced them was a planetary phenomenon, not a local one. Sea level rose dramatically as the Sturtian and Marinoan ice sheets melted. The calculations are uncertain, but estimates suggest that the volume of water stored in cryogenian ice sheets, if comparable to the ice volumes inferred from the geological evidence, could have raised global sea level by 500 to 1500 meters relative to its glacial minimum. That is an extraordinary number, far exceeding even the most extreme sea level changes of the Pleistocene, and it produced a transgression of the ocean over low-lying continental areas that would have been exposed as dry land during the glacial maximum. The cap carbonates were deposited during and immediately after this transgression, their distributions reflecting the progressive flooding of continental margins by a rising ocean as the ice retreated. A 2024 study from Columbia University re-examined the processes driving the post-Marinoan ultra-greenhouse period, using new geochemical data from cap carbonate sequences in Namibia and China. The study's conclusions challenged some of the more extreme estimates of post-glacial carbon dioxide concentrations. The geochemical evidence from the cap carbonates, specifically the carbon and calcium isotope ratios, is more consistent with a greenhouse aftermath that was intense but relatively short-lived, less extreme in its temperature peak than the most dramatic model scenarios had suggested. The study also emphasized the role of pre-existing ocean alkalinity accumulated during the glaciation from submarine volcanic weathering. The cap carbonates, in this view, were not produced solely by continental weathering inputs after deglaciation. They were the product of an ocean chemically primed throughout the glaciation to precipitate carbonates at the first opportunity. The strontium isotope record embedded in cap carbonates and post-glacial sediments tells a complementary story about weathering rates in the aftermath of deglaciation. Strontium has two relevant isotopes: strontium-87, derived from the decay of rubidium in old continental crust, and strontium-86, derived primarily from young mantle material through submarine volcanic activity. The ratio of these two isotopes in seawater reflects the balance between continental weathering input, which delivers radiogenic strontium-87, and seafloor hydrothermal input, which delivers non-radiogenic strontium-86. In the cap carbonates and immediately overlying sediments of both the Sturtian and Marinoan, the strontium isotope ratio shifts rapidly toward more radiogenic values, evidence for an enormous pulse of continental weathering input to the ocean as glacial sediments were exposed and dissolved by acidic post-glacial rain. The pulse is visible in the rock. It confirms, independently of the carbon isotope evidence, that the chemistry of the post-snowball world was driven in large part by the rapid weathering of glacially exposed continental surfaces. The cap carbonates are not just a local curiosity or a stratigraphic marker. They are a chemical summary of everything that happened during the glaciation: the suppressed weathering, the accumulated volcanic carbon dioxide, the altered ocean chemistry, the massive sea level rise, the planetary reorganization of thermal structure and atmospheric circulation in the aftermath. All of it compressed into rock layers that in some sequences reach 200 meters in thickness, and that formed, by geological standards, almost overnight. Stand in front of one of those outcrops and you are standing in front of a record of the most rapid and extreme chemical event in the Neoproterozoic record. The glacial sediment below the contact represents 57 million years of frozen conditions. The cap carbonate above it represents a few thousand years of violent chemical change. The boundary between them is a line you could cover with your thumb. Glaciers are not gentle. They move slowly, measured in meters per year, rather than in any speed that registers as motion on a human timescale. The force they apply to the rock beneath them is enormous. Hundreds of meters of ice pressing down on bedrock, grinding stone against stone, pulverizing it into fine powder, abrading it into the angular fragments called till, scraping and shattering and chemically exposing surfaces that had not been in contact with water or air for millions of years. A glacier moving across continental crust does not merely travel over the landscape, it processes it. And what it processes, it eventually delivers to the ocean. When the Sturtian and Marinoan ice sheets retreated, they left behind an enormous quantity of glacially processed rock, ground-up sediment rich in the chemical elements locked within it, freshly exposed surfaces with high weathering reactivity. The landscape was entirely stripped of any soil or vegetation that might have slowed the movement of dissolved minerals into rivers and eventually into the sea. The post-glacial runoff that produced the cap carbonates was not just calcium and magnesium. It carried the full chemical inventory of the rock that had been ground up over 57 million years of glaciation, and two elements in that inventory would turn out to matter more than any others for what came next. The first was phosphorus. Phosphorus is the limiting nutrient in most marine ecosystems over geological timescales. It is essential for every living cell, a component of DNA, of RNA, of ATP, the molecule that transfers chemical energy within cells, of the phospholipids that form cell membranes. Life cannot be built without it, and the rate at which phosphorus is available in the ocean sets a ceiling on how much primary productivity the ocean can support. Under normal conditions, phosphorus enters the ocean primarily through continental weathering, carried in rivers from eroding rock and soil to the sea. The rate is relatively steady, constrained by the pace at which weathering proceeds on vegetated, soil-covered continental surfaces. The post-snowball world had no soil, no vegetation, nothing to slow the erosion of freshly exposed glacial rock. The rivers running off the retreating ice sheets were carrying dissolved phosphorus into the ocean at rates that normal continental weathering would never produce, loaded with the accumulated weathering products of a glacially processed landscape. When that phosphorus reached the ocean, already warm from the post-glacial greenhouse, already rich in the carbon dioxide that serves as the raw material for photosynthesis, the biological response was rapid. Cyanobacteria and early photosynthetic eukaryotes, long constrained by nutrient limitation, encountered conditions that allowed explosive population growth. Primary productivity surged, and as it surged, so did oxygen production. Because photosynthesis produces oxygen as a byproduct, and more photosynthesis means more oxygen entering the atmosphere and the ocean. Studies of Ediacaran age sediments from multiple continents have found evidence for post-glacial nutrient enrichment in the expected chemical signatures, elevated phosphorus concentrations in fine-grained marine sediments, carbon isotope ratios consistent with high biological productivity, and sedimentary textures suggesting rapid accumulation of organic matter. The Doshantuo Formation in South China, one of the most intensively studied Ediacaran rock sequences in the world, preserves phosphorite deposits, rock composed primarily of calcium phosphate minerals, formed when phosphorus concentration in the water column becomes high enough to precipitate chemically rather than simply accumulating in sediment. Phosphorites are rare in the geological record. Their presence in the early Ediacaran is a geochemical flag marking an ocean that was, for a period, genuinely overloaded with phosphorus from glacial sources. The second element is copper, and its story is less intuitive but potentially just as important. Copper is a trace metal, present in seawater in extremely small concentrations, measured in nanomoles per litre rather than in the grams per litre quantities of the major dissolved constituents. At those concentrations, it is not a nutrient in the conventional sense, yet copper is an essential component of several classes of proteins that sit at the intersection of oxygen chemistry and cellular metabolism. Ceruloplasmin and related copper-containing enzymes play central roles in managing the toxicity of reactive oxygen species, the chemically aggressive byproducts of aerobic metabolism that can damage DNA and proteins if not neutralized. Cytochrome C oxidase, the terminal enzyme in the mitochondrial electron transport chain, requires copper at its active site. Lysyl oxidase, which is involved in cross-linking collagen and elastin, the structural proteins that give animal tissues their mechanical integrity, requires copper for its function. Without adequate copper, the biochemical machinery of complex aerobic life runs into serious constraints. Many Sturtian glacial deposits around the world, in Greenland, in North America, in Australia, across parts of Africa, sit directly on or in close proximity to copper mineralized rock. The Franklin Large Igneous Province, whose weathering contributed to the onset of the Sturtian in the first place, contains copper-bearing mineral deposits. As the Sturtian ice sheets advanced across these copper-rich terrains and then retreated, they processed that rock in the same way they processed everything else, grinding it, exposing fresh surfaces, delivering the dissolved copper into drainage systems that eventually reached the sea. Modeling of cryogenian ocean chemistry suggests that dissolved copper concentrations in the post-Sturtian ocean were substantially elevated above background levels. Those elevated concentrations persisted, declining only slowly as the ocean chemistry re-equilibrated, into the Ediacaran and, by some estimates, through into the early Cambrian. The timing of this copper enrichment overlaps with the period in which animal life was first diversifying. The proteins that require copper for their function are not peripheral to animal biology. They are central to it, to the management of the oxygen that fuels aerobic metabolism, to the structural proteins that make animal bodies possible, to the enzyme systems that support complex tissue differentiation. Elevated copper availability in the ocean would not, on its own, have produced animals, but it would have removed a potential bottleneck, a chemical constraint on the assembly of the protein machinery that animal complexity requires. Oxygen itself rose through the Ediacaran in what the geochemical record suggests was a two-stage process. The first stage, following the Marinoan deglaciation and the phosphorus-driven primary productivity surge, brought atmospheric oxygen to levels that were above the low cryogenian baseline, but still well below the modern concentration. This first oxygenation pulse correlates broadly with the appearance of the first large sessile Ediacaran organisms, animals or animal-like forms that could survive in oxygen-poor water by being immobile and keeping their metabolic demands low. The second stage, occurring later in the Ediacaran and extending into the early Cambrian, brought oxygen closer to modern levels and correlates with the appearance of motile, predatory, and skeletonized animal forms that require both higher ambient oxygen concentrations and the copper-dependent proteins needed to process it efficiently. The glaciers did not plan any of this. Ice has no intentions. The connection between cryogenian glaciation and the chemical preparation of the post-glacial ocean for complex life is not teleological. It is mechanical. Ice ground rock. Rock contained phosphorus and copper. Meltwater delivered those elements to the ocean. The ocean chemistry changed. The organisms present in that changed ocean responded to changed conditions in the only way organisms respond to anything, through differential survival and reproduction across the millions of years that the new chemistry persisted. What emerged from that process, slowly and without direction, was a world chemically suited to a kind of life that had not existed before. The ocean was now chemically different, phosphorus-loaded, copper-rich, newly oxygenated, warmer than it had been in tens of millions of years. The organisms that had survived the Sturtian entered it. For roughly 1 billion years before the glaciation, nothing had happened, not in terms of organismal complexity. That is not quite accurate. An enormous amount happened during the Proterozoic, from the Great Oxidation Event to the assembly and breakup of supercontinents, to the diversification of eukaryotic cell types into forms of increasing internal complexity. But in terms of the organizational level of life, the question of whether organisms were built from one cell or from many cooperating cells working together as a unit, nothing happened. Eukaryotes had existed since at least 1.8 billion years ago. They had evolved nuclei, mitochondria, complex cytoskeletons, the capacity for sexual reproduction. They had diversified into hundreds of lineages, and for 1 billion years, every one of them remained resolutely single-celled. Then, within a geologically narrow window spanning the Cryogenian and early Ediacaran, multicellularity appeared independently in at least 3 separate lineages: the ancestors of animals, the ancestors of plants, and the ancestors of fungi, not sequentially in a chain where one lineage learned the trick and passed it to the others. Independently and roughly simultaneously, in organisms that shared a common ancestor hundreds of millions of years earlier and had been diverging ever since. The coincidence demands an explanation, and for decades the best available answer, that rising oxygen levels provided the necessary biochemical conditions, felt incomplete. Oxygen was rising through much of the Proterozoic, long before multicellularity appeared. Why then? Why all 3 lineages at once? The question has driven some of the most creative theoretical work in evolutionary biology over the past decade, and the answers that have emerged are not what anyone initially expected. A 2024 study from researchers at MIT and the Santa Fe Institute, published in Proceedings of the Royal Society B, built a mechanistic model of how Snowball Earth's physical conditions could have generated selective pressure favoring multicellularity. The specific target was eukaryotic heterotrophs, organisms that obtain energy by consuming other organisms rather than by photosynthesis. The model starts with what snowball conditions did to the ocean: lower temperatures slowing metabolic rates, reduced light limiting primary productivity, nutrient scarcity constraining population sizes across the food web. These conditions affected single-celled prokaryotes and eukaryotes differently, because the 2 groups occupy different physical regimes when it comes to how they acquire nutrients from the surrounding water. Small cells, below a critical size threshold, live in what physicists call the diffusive regime. Nutrients reach them primarily by diffusion, the random thermal motion of molecules through the surrounding fluid, rather than by directed flow. In the diffusive regime, smaller is generally better. A smaller cell has a higher surface area to volume ratio, which means a proportionally larger surface through which nutrients can diffuse, and it generates less of the thin layer of nutrient-depleted water that surrounds any cell consuming dissolved molecules from the medium. Prokaryotes, which are small, are well adapted to the diffusive regime. They were favored, under snowball conditions, by selective pressure toward even smaller size and higher surface area. Eukaryotic heterotrophs were in a different position. They were already larger than prokaryotes, already pushed into the boundary between the diffusive regime and the motile regime. In the motile regime, organisms are large enough to swim through their environment, creating flow around themselves and accessing nutrients over a larger volume of water than diffusion alone would supply. In the motile regime, larger is generally better because a larger organism can generate more flow, cover more volume, and intercept more food particles per unit time. The snowball conditions that pushed prokaryotes towards smaller size pushed eukaryotic heterotrophs in the opposite direction, toward larger size, and toward the organizational changes that larger size requires. A single large eukaryotic cell faces physical problems that a colony of coordinated smaller cells does not. Nutrient transport from the cell surface to the interior becomes less efficient as cell volume increases because the diffusion distance from surface to center grows with cell radius. Structural integrity becomes more difficult to maintain. Reproduction becomes slower. The solution that the model identifies and that William Crockett, the study's lead author, described as counterintuitive, involves two interacting factors. Cold ocean water increases viscosity, changing the physical regime of nutrient uptake. Resource scarcity intensified competition for whatever food was available. Under both pressures simultaneously, the optimal response for a eukaryotic heterotroph was not to remain as a single large cell. It was to become a coordinated multicellular aggregate, a hollow sphere of cells, each contributing to the collective's movement and nutrient acquisition, sharing the metabolic and reproductive burden. The model organism the researchers used to illustrate this is what they called a chonoblastula, a hollow sphere of chonoflagellate-like cells resembling the embryonic blastula stage of modern animals and the colonial forms of modern chonoflagellates, which are among the closest living relatives of animals. The chonoblastula in the model was not a biological curiosity. It was the optimal shape for a heterotrophic organism trying to generate directed flow for feeding in a cold, viscous, nutrient-poor ocean. The transition from a single large cell to a coordinated hollow sphere of smaller cells, the fundamental architectural shift that underlies animal development, was not, in this framework, a random innovation that happened to be advantageous. It was a predictable response to a specific set of physical boundary conditions that Snowball Earth imposed. What makes this model compelling beyond its internal logic is the timing it predicts. The cryogenian boundary conditions that the model identifies as driving the transition were present from roughly 717 million years ago, when the Sturtian glaciation began, through the end of the Marinoan around 635 million years ago. The interglacial between the two glaciations, the warm interval from roughly 660 to 650 million years ago, would have briefly relaxed those conditions before reimposing them. The molecular clock estimates for the divergence of animal, plant, and fungal multicellular lineages cluster around this interval with a precision that, given the uncertainties in molecular dating, is consistent with a cryogenian origin for all three transitions. The timing, the mechanism, and the phylogenetic pattern all align. The cryogenian gap, the interglacial interval between the Sturtian and Marinoan, deserves particular attention in this context. The warm, nutrient-loaded ocean of the interglacial, following the chemical disruption of the Sturtian deglaciation, provided conditions quite different from the cold, oligotrophic environment of the glaciation itself. Organisms that had been selected for multicellular organization under snowball conditions were now released into a warmer, richer environment. The earliest fossil evidence for multicellular algae with differentiated cell types appears in sediments from this interval, suggesting that the biological potential for multicellularity, shaped by snowball pressure, was first expressed visibly in the fossil record during the brief window between the two glaciations. None of this is settled science. The MIT and Santa Fe model is a theoretical framework, not a direct measurement of cryogenian organisms. The molecular clock estimates carry substantial uncertainty. The causal connection between Snowball Earth physical conditions and the specific timing of multicellular transitions in three independent lineages remains, at the level of direct evidence, unproven. What the model provides is a mechanistic explanation for a coincidence that had previously lacked one. It accounts for why the conditions of the cryogenian would specifically favor the organizational change that multicellularity represents, in organisms already positioned at the physical threshold where that change becomes advantageous. The question of why it took 1 billion years is the same as the question of why it happened when it did. For 1 billion years the conditions were not right. Then they were. The Ediacaran period begins at 635 million years ago, defined by the termination of the Marinoan glaciation and the deposition of the cap carbonate that marks it globally. It ends at 538.8 million years ago at the boundary with the Cambrian. In between 96 million years of geological time, the fossil record of complex, macroscopic, multicellular life begins, not with a bang, with something stranger. The organisms preserved in Ediacaran rock sequences around the world do not look like the ancestors of anything familiar. They are not the precursors of fish or worms or corals in any obvious morphological sense. They are fronds and discs and quilted mattress-like forms, organized by a body plan logic that has no direct modern analogue and that has resisted confident taxonomic assignment for the 7 decades since the first specimens were formally described. Some of them were sessile, permanently attached to the seafloor, filter feeding or absorbing dissolved organic matter from the water above them. Some moved, leaving trace fossils that record directed locomotion through soft sediment. Some were flat and leaf-like, growing to a meter or more in length. Some were small and disc-like, a few centimeters across, their internal structures visible in fossils of extraordinary preservation quality. None of them had eyes or jaws or mineralized shells or the segmented body plans that would characterize the fauna of the subsequent Cambrian. The Ediacaran Hills in South Australia gave the period its name, but the biota was not recognized as geologically significant until the 1940s and 1950s, when Reginald Sprigg, working for the South Australian government, found large disc-like impressions in the Pound quartzite. Sprigg thought he had found Cambrian fossils. He was off by roughly 30 to 40 million years. The material he collected eventually contributed to the recognition that a complex, macroscopic biota had existed before the Cambrian, a discovery that required revising a long-standing assumption in paleontology about the nature of the Precambrian fossil record. Mistaken Point, on the southeastern coast of Newfoundland, has since become one of the defining localities for understanding Ediacaran ecology. The fossils there, preserved under volcanic ash falls that buried entire seafloor communities where they lived, date to approximately 565 million years ago and represent one of the oldest known assemblages of large, frond-like organisms. The Mistaken Point fossils are deep water forms, preserved in what was clearly a low-oxygen, low-energy seafloor environment far from any shore, suggesting that the Ediacaran biota was not confined to shallow coastal settings, but occupied a range of marine environments, including the deep water communities that rarely preserve well. The ash layers that killed and preserved these communities did paleontology an inadvertent service. They provide the kind of rapid burial that fossilization requires, preserving soft-bodied organisms that would otherwise leave no record at all. The Russian White Sea region preserves a somewhat younger Ediacaran assemblage, dating to roughly 555 to 560 million years ago, that has been collected and studied intensively since the mid-20th century. The White Sea fauna includes Dickinsonia, one of the most iconic and most debated organisms in Ediacaran paleontology. Dickinsonia is broadly oval, bilaterally symmetric, covered in a pattern of parallel ridges separated by a central midline, and ranges in size from a few millimeters to over a meter. For decades it was classified variously as a worm, a cnidarian, a lichen, and a member of an entirely extinct kingdom of organisms with no modern relatives. In 2018, a study published in Science reported the detection of cholesterol biomarkers in exceptionally preserved Dickinsonia specimens from the White Sea, molecules that are produced exclusively by eukaryotes and specifically by animals. Dickinsonia, after decades of uncertainty, appears to have been an animal, or at least an animal-grade organism. What kind of animal remains unclear. It has no obvious homologue in the modern biosphere. Kimberella, also from the White Sea, is less ambiguous in at least one important respect. It left feeding traces. The small shield-shaped organism appears to have moved across the seafloor and scraped microbial mats from its surface using a structure resembling a radula, the ribbon-like feeding organ characteristic of mollusks. If Kimberella was indeed using a radula, it was a bilaterian animal, belonging to the same major group that includes all modern animals with a distinct front and back end, and potentially a relative of the mollusk lineage. The trace fossils associated with Kimberella specimens are among the most compelling pieces of evidence that directed purposeful animal movement existed in the Ediacaran well before the Cambrian. The carbon isotope record through the Ediacaran is not stable. It oscillates through a series of anomalies, large globally distributed excursions in delta-13 carbon that reflect disruptions to the marine carbon cycle of a magnitude rarely seen in later geological periods. The Churam-Wanoka anomaly, the largest negative carbon isotope excursion in the entire geological record, occurs around 565 to 550 million years ago within the Ediacaran. Its cause is debated, but most interpretations involve a major perturbation to the organic carbon cycle, either the oxidation of a large dissolved organic carbon reservoir that had been accumulating in the ocean, or a significant change in the rate of organic carbon burial, or some combination of both. Whatever caused it, the Churam-Wanoka anomaly is a global signal, preserved in Ediacaran sections on every continent, indicating that the marine carbon cycle was still far from the stable, well-buffered system that characterizes later geological periods. Oxygen continued rising through the Ediacaran unevenly. Geochemical proxies for ocean oxygenation, iron speciation data, molybdenum and uranium concentrations in black shales, the distribution of redox-sensitive trace metals, indicate that the Ediacaran ocean was chemically heterogeneous in a way that the modern ocean is not. Oxygenated surface waters and shallow coastal settings coexisted with a deep ocean that remained largely anoxic, with anoxic and even euxinic, sulfide-rich conditions expanding and contracting in response to changes in productivity and circulation. The organisms living in this chemically variable ocean were navigating an environment in which the availability of oxygen was patchy and unpredictable in ways that modern marine organisms do not experience. The end of the Ediacaran is marked by an extinction, not the gradual disappearance of organisms as the environment changed around them, but a relatively rapid loss of most of the characteristic Ediacaran fossil types from the record, occurring around 539 million years ago. What replaced them was so different in its organization and ecological relationships that the transition stands as one of the most significant boundaries in the history of life. The small shelly fauna of the earliest Cambrian came first, then the full complement of animal body plans that appear over the following 20 million years. What the Ediacaran organisms were precisely remains contested. Whether most of them were animals or proto-animals, or something else entirely that has no modern equivalent and left no living descendants, a failed experiment in multicellular organization, in the memorable phrase of one paleontologist, is a question the fossil record has not yet answered with finality. What is not contested is their significance as evidence. They are the first complex, macroscopic, multicellular organisms to leave a substantial and globally distributed fossil record. They existed. They diversified across 100 million years of Ediacaran time. And then, for reasons that are still being worked out, most of them disappeared, leaving behind an ocean that was, within a geological eye blink, populated by things that ate each other. That transition was coming. The Ediacaran was the last quiet chapter before it. The Ediacaran organisms ate, or absorbed, or simply persisted, and then most of them were gone. What followed them was so different that the boundary between the two worlds has its own name, the Cambrian. What produced that boundary, and what drove the remarkable expansion of animal life that came with it, is a question that loops back in multiple ways to where this documentary began. Science proceeds by replacing large uncertainties with smaller ones. The Snowball Earth hypothesis, as it stands in 2026, is not a finished theory. It is an actively contested framework that has survived decades of testing, accumulated a substantial body of supporting evidence, and generated enough anomalies and unresolved questions to keep several generations of researchers occupied. Understanding which parts of the hypothesis are well established, which remain genuinely uncertain, and which are still actively debated is essential. Snowball Earth is not a confirmed historical fact known in all its details. It is a scientific picture that is more resolved in some places than others. The existence of at least 2 global or near-global glaciations during the Cryogenian is not seriously disputed in the current literature. The paleomagnetic evidence for equatorial glaciation, the global synchrony of glacial deposits established by geochronology, the banded iron formations, the cap carbonates. These lines of evidence are robust and mutually consistent. The scientific community has moved past the question of whether the Sturcian and Marinoan glaciations were extraordinary events. They were. The question of how complete the ice cover was is a different matter. The hard snowball and the slush ball remain genuinely competing hypotheses. The hard snowball, complete or near-complete ice cover from pole to equator, with no permanently open water anywhere at the surface, is the version of the hypothesis that produces the most dramatic predictions and has the most straightforward connection to the climate physics. The ice albedo feedback, if allowed to run to completion, should produce exactly this. Climate models consistently show that once the feedback passes the critical latitude threshold, the planet moves rapidly to a fully ice-covered state with no intermediate stable configuration. The hard snowball is, in this sense, the physically predicted outcome. The slush ball persists because of life, specifically because the organisms that existed before the glaciations were present, in some form, on the other side. And because some of those organisms, particularly the photosynthetic eukaryotes, require light to survive. A completely ice-covered planet with kilometre-thick equatorial ice and no open water is difficult to reconcile with the survival of any photosynthetic lineage, even accounting for the refuge mechanisms discussed earlier. The presence of photosynthetic biomarkers in Marinoan age sediments from low paleolatitude locations strengthens the slushball case. The climate models that favour hard snowball conditions have difficulty explaining this evidence. The models that allow for thin equatorial ice have difficulty explaining how the ice albedo feedback failed to complete itself. Neither model wins cleanly. The current consensus, to the extent one exists, is that the Marinoan glaciation may have been somewhat less complete than the Sturcian, that the planet's second freezing may have left a narrow equatorial band of thin or seasonally open ice, while the first was genuinely or near genuinely complete. This is speculative. The distinction between hard snowball and slushball may also be less absolute than the models suggest, with reality falling somewhere in a continuum that neither end member fully captures. The trigger for the Sturtian glaciation is better constrained than the trigger for the Marinoan, but neither is fully resolved. The Franklin Large Igneous Province eruption around 718 million years ago and the carbon dioxide drawdown that accelerated silicate weathering of its basaltic rocks provides a plausible and mechanistically coherent explanation for the Sturtian onset. The 2024 Adelaide and Sydney study on mid-ocean ridge carbon dioxide output being anomalously low during this period adds another dimension. But the exact sequence of events, what tipped the climate system past the critical threshold at that specific moment, rather than 10 million years earlier or later, is not fully resolved. The Sturcian onset remains a subject of ongoing geochronological and modelling work. The Marinoan trigger is even less clear. The interglacial between the two glaciations lasted somewhere between 10 and 30 million years, during which carbon dioxide levels were high and the climate was warm. What drew carbon dioxide down again sufficiently to cross the threshold for a second time? Whether it was silicate weathering of the cap carbonate sequences and newly exposed continental rock, or a reduction in volcanic outgassing, or some combination, is debated. The patchiness of the interglacial sedimentary record makes it difficult to reconstruct the geochemical evolution of this interval in sufficient detail to distinguish between competing explanations. The duration of the Sturtian glaciation, 57 million years, raises its own questions. How did the carbon dioxide escape mechanism not terminate the glaciation sooner? Volcanic outgassing continued throughout the Sturtian, and models of carbon dioxide accumulation against a sealed surface suggest that the concentrations required for deglaciation should have been reached in somewhere between 4 and 30 million years. If the Sturtian lasted 57 million years, either the models are overestimating volcanic output or underestimating the carbon dioxide concentration required for deglaciation. Alternatively, some mechanism was actively removing carbon dioxide from the atmosphere during the glaciation, perhaps submarine weathering of basalt at mid-ocean ridges, which continues even under glacial conditions and can draw carbon dioxide out of seawater. A 2024 model from the University of Leeds suggests this seafloor weathering was more efficient during snowball conditions than previously assumed, potentially extending glaciation duration. The question is not resolved. The relationship between Snowball Earth and the evolution of complex life is the most exciting open question of all. It sits at the intersection of geology, evolutionary biology, and biophysics, and the answer matters for understanding not just Earth's history, but the conditions that might support complex life elsewhere. The correlations are clear. The cryogenian glaciations coincide with molecular clock estimates for the origin of multicellular animal, plant, and fungal lineages. The post-glacial chemical enrichment of the ocean with phosphorus and copper coincides with the early Ediacaran diversification. The Ediacaran biota appears in the fossil record in the interval between the end of the Marinoan and the Cambrian explosion. Whether these correlations reflect causation, whether Snowball Earth actually drove the evolution of complex life rather than merely coinciding with it, is not proven. Correlation is not causation, and the evolutionary processes involved were operating over tens of millions of years on populations and lineages whose history we can only partially reconstruct. The MIT and Santa Fe Institute model of snowball-driven multicellularity is theoretically rigorous and mechanistically coherent, but it is a model. Direct evidence that cryogenian physical conditions specifically selected for multicellular body plans, rather than contributing to a more complex set of factors that included rising oxygen, changing continental configurations, and ecological dynamics internal to the evolving biota, does not yet exist in a form that settles the question. What does exist is a narrative that is more coherent, more mechanistically grounded, and better supported by multiple independent lines of evidence than any alternative explanation for the timing and character of the Ediacaran and Cambrian diversifications. The Snowball Earth hypothesis does not explain everything. No single geological event can, but it explains a remarkable amount: the chemical disruption of the ocean, the nutrient pulse, the selective pressure on cell organization, the timing of oxygenation, the conditions in which the first complex animals appeared, with a consistency that has survived 40 years of active testing. The questions that remain are not reasons to doubt the framework. They are the frontier of what the framework is still working to understand. Science happens in papers and in models, but it begins in the field. The understanding of Snowball Earth that has accumulated over the past 4 decades was built, piece by piece, by researchers who travelled to remote locations on multiple continents, collected samples from outcrops that no road reached, and spent years analysing what those samples contained. The field sites where the critical evidence was gathered are not just locations on a map. They are the physical places where the past becomes legible, where a geologist can stand in front of a rock face and read, in the layers and colours and textures of the stone, the history of a planet 700 million years ago. The Flinders Ranges of South Australia are the canonical Snowball Earth locality. The ranges run roughly north-south for over 400 kilometres through the arid outback of South Australia, their ridges and gorges exposing some of the best preserved Neoproterozoic rock sequences on the planet. The Elatina Formation's glacial diamictites, the Nuckalina Cap dolostone with its tubestone stromatolites and giant wave ripples, the Brachina Gorge sections sampled for carbon isotopes by dozens of research groups. All of these are accessible from the wilderness of Ediacaran Ranges National Park. The park is remote by ordinary standards. By geological fieldwork standards, it is practically convenient. George Williams, whose decades of work on the Elatina's tidal rhythmites contributed to the low-latitude paleogeographic reconstruction, made the Flinders Ranges his primary field area for much of his career. The rocks there are not difficult to find. Reading them correctly took most of a century. The Garvalach Islands off the west coast of Scotland are less visited, but arguably more complete in their cryogenian record. The islands, Garb Eilich, Achuli, Dun Chonuil, Eilich and Nauim, are accessible only by boat from the port of Creove Haven on the Argyll coast, and landing conditions depend on weather and sea state in ways that have limited fieldwork there to brief summer windows. The Port Ascaig Formation's 1.1 kilometre thickness of Sturtian age glacial sediment, topped by pre-glacial tropical carbonates at its base and capped by post-glacial sediments above, is exposed in sea cliffs and shoreline outcrops that require scrambling over tide-washed rock to reach. The 2026 study that identified annual varve cycles in the Port Ascaig Formation involved collecting samples from sections that geologists had visited many times before. The new result came not from finding new outcrops, but from applying new analytical techniques to material that had been known for decades. The Mackenzie Mountains of Canada's Northwest Territories hold the Sturtian type section, the stratigraphic sequences that define the Sturtian glaciation and from which many of the key geochronological constraints have come. The Rapitan group, with its thick, banded iron formation sequences and diamictite beds, outcrops in river valleys and ridgelines that are reached by bushplane from Yellowknife, or by multi-day hiking through wilderness that sees almost no traffic outside the summer field season. Francis MacDonald spent multiple field seasons here in the years leading up to his 2010 synthesis, dating volcanic ashbeds within the Sturtian sequences with the uranium-lead precision that established the global synchrony of the glaciation. The logistics of working in the Mackenzie Mountains, the weather, the remoteness, the bears, the narrow window between snowmelt and the first autumn freeze, are standard features of high-latitude geological fieldwork, neither exceptional nor comfortable. Namibia provided Paul Hoffman with the evidence that transformed Snowball Earth from a minority hypothesis into a serious scientific framework. The Namibian sequences, the Gorb Formation glacial diamictites, and the overlying Kyleberg Cap dolostone in the Otavi mountainland are exposed in the dry hills of northern Namibia. Hoffman and his collaborators explored this terrain during field campaigns that began in the 1990s and eventually accumulated to over 50 months of total field time. Hoffman's 1998 science paper, co-authored with geochemist Dan Schrag and two colleagues, drew on this fieldwork to make the comprehensive case for Snowball Earth that finally forced the hypothesis into mainstream discussion. The Kyleberg Cap dolostone, with its negative delta 13 carbon values and its sharp contact with the underlying glacial sediment, is one of the defining outcrops in the entire Snowball Earth literature. Hoffman has described the moment of understanding what that contact meant as one of the clearest experiences of scientific recognition he had ever had. The sense of seeing, in rock, the answer to a question that the geological community had not yet thought to ask. The Dushantuo Formation in Guizhou Province, China, has become one of the most intensively studied Ediacaran rock sequences in the world since the 1990s. When Chinese and international researchers began systematic sampling of its remarkable preservation. The formation's phosphorite beds preserve cellular-level detail of early Ediacaran organisms, embryo-like clusters of cells, algal fronds, and what may be early animal tissues, in a quality of three-dimensional mineralization that has no parallel in any other Ediacaran locality. Reaching the best Dushantuo sections involves travel to villages in rural Guizhou that are not served by major roads, followed by hiking to roadside and riverside cliff exposures where the phosphorite beds are accessible. The extraordinary preservation of the Dushantuo material, and the equally extraordinary debates over what the preserved organisms actually are, have made this formation a central battlefield in the ongoing argument over the nature and affinities of Ediacaran life. The Gasquias Formation in Newfoundland preserves the record of the post-Marinoan glaciation of the same name, and the Mistaken Point Ecological Reserve on the Avalon Peninsula holds the oldest known community of large, frond-like Ediacaran organisms anywhere in the world. Mistaken Point is a UNESCO World Heritage Site, and access to the most sensitive fossil surfaces is managed by provincial authorities. Guided tours are required, and independent sampling is not permitted. The fossils are preserved in situ in near-horizontal surfaces of volcanic ash and underlying mudstone, their shapes pressed into the rock with a clarity that has made the site famous among paleontologists and accessible to non-specialists in a way that few other Ediacaran localities can match. The researchers who first worked out the taxonomy and ecology of the Mistaken Point assemblage, Goethe Kluesendorf, Guy Narbonne and their collaborators, spent years visiting the site in conditions that included Newfoundland fog, Atlantic wind, and the persistent possibility of rain at any moment. The research community that has built the Snowball Earth framework is not large by the standards of the natural sciences. It overlaps substantially across subfields. The same names appear in geochemistry papers, paleomagnetics papers, modelling papers, and paleontology papers because the questions involved require competence across all of these areas simultaneously and the community small enough that people know each other's work in detail. Hoffman, Kirschvink, MacDonald, Bowring, Halverson, Shields, Evans, Narbonne, Knoll. These are researchers whose careers have been substantially defined by the Snowball Earth problem. They have argued with each other in print and at conferences for decades. Their collective fieldwork has taken them to every continent and produced the evidence base that makes the hypothesis defensible. The argument continues. New field campaigns are being planned. New samples from old outcrops are being analysed with techniques that were not available when those outcrops were first visited. The cryogenian rock record has not been exhausted. There are sections in Greenland, in Brazil, in Central Africa, in northern Russia that have received less systematic attention than the canonical localities, and that may yet yield information that refines or revises the current picture. The history of Snowball Earth research is a history of surprises, of results that contradicted expectations, of evidence that arrived from unexpected directions, of hypotheses that were modified or replaced as new data accumulated. That process is not finished. The rocks have more to say. There is a particular quality to the silence that comes after a long journey through geological time. Not emptiness. Something closer to the feeling of having set down a very heavy thing. The accumulated weight of billions of years, of extinctions and freezings and thawings, of organisms that survived conditions that should have ended them. A planet that has been in its long history so many different things than it is now. You have been carrying that weight through 16 chapters. The equator buried under a kilometre of ice. The ocean sealed, dark, iron-rich, patient. The volcanoes continuing their indifferent work. The organisms holding on in hydrothermal darkness and dusty meltwater pools and thin equatorial seas. The ice retreating, the world warming into something that had not existed before. You can set it down now. The story of Snowball Earth does not resolve into a clean lesson. It is not a parable about resilience, though resilience was required. It is not a warning about climate, though climate was central. It is not a triumphant narrative about the inevitable march toward complexity, though complexity is where things eventually went. It is something more honest than any of those framings. The record of what actually happened, reconstructed from the physical evidence that the planet preserved for 700 million years, interpreted by researchers who spent their careers in difficult places asking the rocks what they remembered. What happened was this. A supercontinent broke apart in the right configuration at the right time, weathering its own basalts in tropical rain, drawing carbon dioxide from an atmosphere that had no way to replace it quickly enough. The planet crossed a threshold it had not crossed in over 2 billion years, and the ice albedo feedback carried it to the equator in less time than the geological record can resolve. For 57 million years, the surface was frozen. Life persisted in the places the ice could not reach, in the dark water above hydrothermal vents, in subglacial lakes warmed by the slow decay of radioactive rock, in seasonal meltwater pools on ice surfaces darkened by volcanic dust. Possibly in a thin equatorial band of sea where the sun still reached water. The volcanoes continued. The carbon dioxide accumulated. Eventually the threshold was crossed again, and the ice retreated in geologically near instantaneous time, leaving behind an ocean loaded with phosphorus and copper and dissolved iron, warm and nutrient-rich, and chemically unlike anything that had existed for tens of millions of years. Into that ocean, something changed. The eukaryotes that had been single-celled for 1 billion years, waiting, in no meaningful sense of waiting, for conditions that would make a different organizational strategy advantageous, encountered those conditions. The physics of nutrient acquisition in cold, viscous water selects for coordinated multicellular aggregates over single large cells. Elevated copper made the protein machinery of aerobic complexity more accessible. Elevated phosphorus fed the primary productivity that drove oxygen upward. The lineages that would become animals and plants and fungi began the organizational transitions that would take another 100 million years to fully express. And then the planet froze again. The Marinoan glaciation did not undo what the Sturtian had started. It continued the selection for another 15 to 20 million years for the organisms that could survive by whatever means the frozen world allowed. When it ended, the ocean it left behind was, if anything, more chemically altered than the one the Sturtian had produced. The cap carbonates were thicker, the nutrient pulse was larger. The Ediacaran period that followed was populated by organisms, fronds and discs and quilted forms of uncertain affinity that represented the first substantial experiment in macroscopic multicellular life, and that persisted and diversified for almost 100 million years before being replaced by the fauna of the Cambrian. The planet you live on is the downstream consequence of all of this. Not solely. The history of life involves countless contingencies, and the Cambrian explosion and everything that followed it was shaped by ecological and evolutionary dynamics that extend far beyond the cryogenian. The specific timing of the transition from a single-celled to a multicellular world, the specific chemical state of the ocean in which the first animals diversified, all of these trace back to the most extreme climate events the planet has experienced in the past billion years. The post-glacial nutrient pulse, the frozen selection, the iron dark ocean. The evidence increasingly supports the connection. The ice made you possible. Not you specifically, not your particular form or your particular history, but the kind of thing you are. A multicellular organism of significant complexity, built from cells that cooperate and differentiate and maintain tissues and organs, running on aerobic metabolism, capable of the neural activity that makes experience possible. That kind of organism required specific conditions to become advantageous enough to be selected for. The cryogenian provided them. This is not a comfortable thought exactly. There is something vertiginous about tracing the origin of consciousness, of the capacity to lie here, in the dark, aware of your own breathing, back to a frozen planet and a set of physical equations about nutrient diffusion in cold water. The chain of causation is real, and the distance between its beginning and its end is 700 million years. And at the beginning, there was nothing that could have anticipated the end. But the chain is there. The planet froze. Life held on. The ice retreated. The ocean changed. The cells that had been waiting, in no sense waiting, found themselves in conditions that made complexity not just possible but optimal. And from that, over hundreds of millions of years of evolution that the cryogenian set in motion without intending anything, came everything. You are here because the equator was once under ice. Let that be the last thing you think about tonight, not as a weight, but as a kind of anchor. The deep past is not threatening. It is simply immense, immense and patient, and at this distance, very quiet. The planet has been through worse than anything you are carrying into sleep, and it is still here, still tilted on its axis, still circling its star, still covered in the descendants of organisms that survived 57 million years of frozen dark. The ice is gone. The ocean is warm. The night outside is the same night it has always been, old and very still and full of time. Rest now.